Okay. So, welcome to day 2 of workshop 29 for May 2022. The demultiplexing, good practices, hidden surprises, and so on. So we are, I think I originally, yesterday I told you we'd only do 2 days, but now that I see you on material, and what's it going to be, we will do a 3rd day, maybe a 4th day tomorrow, just so you know. It was always on the schedule, but anyway, so this is sort of the revised outline. I haven't really added or deleted anything, I just changed the splits. Okay, so the first thing we're going to do is finish up the end of the single end example we were looking at, the ZVPO 98.1. So just to recap where we were, we had looked at the raw run folder. The lane was originally 51851, but the lane donor has said we got to remove the main ends, so I cut it down to 181, and that's on Hoffman 2 and U-Scratch-C Focus, and it's world readable, and you can grab a copy of that and play with it and run BCL to FASTQ2 yourself. Paradigm run that we'll do today is ZVPO 99. I did not get permission for it, so that one I can't. It's not world readable. It's in that directory, but you won't be able to copy it. So yeah, we started a session in Hoffman. Like I said, the resources can be kind of tricky. If you have a local big Linux machine, just use that instead. It'll be simpler. There, I gotta get my session back to the way we were yesterday. That's just a reminder of the version that's on there. And there's the command line help again, and this is the directory where the stuff is. Okay, and then we had, we then put up command line options for the this cable for the projector is exciting. We talked about command line options, and so we had run BCL to FASTQ2 in the non-Demux mode to get the index reads out, which we then looked at with histograms. That was this pipeline here to generate the histogram, basically use it, paste, cut, sort, unique, awk sort, histogram maker. And then I showed you these 2 little web tools that I made for you guys, the index checker and the universal Demux helper, and introduced you to the idea of kind of looking at that histogram as sort of a major method for sort of figuring out empirically what's going on in the lane. And we decided that these what is it, 21 guys was the things that were empirically present. And let me go back to this red text, which we didn't talk about yesterday, I think, in a second. Let me just finish the recap of kind of what we were doing. And then we looked at the sample sheet that the user submitted. Of course, the sample names and project names have been changed here to protect the lane donor. And then this is an easy one, right? I mean, basically it's a perfect match. The user sample sheet didn't have the 5x1% spike in the core did, so we add that back in. That was the 21st extra guy. And I've put this first column here on Hoffman 2 in this file, just that we have those, and because our R code will need those too. So there's just the list of our 21 targets that we figured out. And then we composed a sample sheet for Demux BCL to FASTQ2. And that is in this file here and looks like this. Okay. And it's just one of these it's very basic, right? Some of this is just part of the format you have to do for BCL to FASTQ2, but you don't need all the other metadata. In particular, please, you probably don't want to include the adapter metadata, because I said you should do your adapter training in a downstream tool. But yeah, the lane numbers here, and then the sample ID, and then the sample name, which I recommend you always take those the same, and then the sample project, which is the directory the files will land in, and the target. I mean, it's basically just the minimal information there. And that's where we were, I think, that's where we left off. So the next thing to talk about is Demux Tolerances, and we'll start in little R analysis. I think I forgot to mention R is kind of a recommended prerequisite for this, but I assume probably all of you guys probably have R experience. It's very, very common in bioinformatics. And so we got to talk about Demux tolerances, and then we'll run the be so fast between Demux mode after that. And then we'll do the paradigm guy. The paradigm guy is pretty involved and interesting, gets an index hopping and so on. So that'll take up most of today. All right, so let me go back to this red text. This red text is just some hints for cases, not just this one. This one was pretty simple, but in general, it's not always completely straightforward to decide what's in there or not. So here's some tips for what you might use guidelines to help decide whether a particular kind of entry in the histogram maybe is something real or not, or is it a variant of something else or what? So, I mean, obviously one of the primary questions is how far is it as a MER, as a K-MER, a sequence from other things that are around, higher frequency things and so on. The empirical Demux helper is the thing that helps you kind of look at that, right? You give it a rank ordered histogram and it starts comparing everybody to the guys before, right? And, or at least the green guys, you can mark and unmark guys at will, compares everybody to the previous green guys. And from that, you can sort of investigate that question of how similar are things to each other, and probably, if you know the design index set, stays at least 3 mismatches apart, but you get things that are 1 mismatch apart in the empirical, probably those things are variants and not real differences. Of course, it gets more complicated if the user has started to mix things with 1 and 2 mismatch conflicts, because now the mix can sort of a priori have things that are close. And now closeness in the empirical is now more problematic because it's not necessarily a killer for not being possible. But anyway, that's one of the primary decision mechanisms. And then you kind of have to judge that one based on the lane's general overall level of index-based call errors and stuff. This was a very clean one pretty much, but you get guys who were sort of very early on in the histogram list. You get lots of variants and maybe even particular cycles of the index reads are sort of bad and whatever. And so that changes your idea of what tolerance you're kind of going to allow, accept as variants of other things. Whereas if it's a very clean run, you may dial your internal tolerance down a little bit. And again, you sort of view this tolerance from the first point in terms of how close the original design was. If the design is like 5 mismatches apart, the full boxes it comes from, and even the full boxes are very far apart, then obviously you're going to be more willing to accept things that are further apart in the empirical list as really just being variants of something else. So these things are just really controlling how you interpret the closeness information. So another primary one you can use is that, is it a well-known sequence, right? So most people are using kits and so on. There's like the Illumina, UDIs, the unique delineities from Illumina. There's the Nextera non-unique set. Whatever boxes and kits that you're using. If you're doing this yourself, of course, you're more connected. You're not, as a core guy, I don't always know exactly what people use because I have to guess or whatever because people don't always tell us. But if you're doing it on your own project or something, you will know or know the person that knows what the kits they use and so on. And so actually you may a priori give more credence to things in the list that actually match things that are known to be in the box. Maybe things that you don't expect to be because it wasn't supposed to be in the mix, but things that are in the box, those are high candidates, for it being extras that shouldn't be there because, it's by random chance, you're not going to have that. So if somebody's used Illumina UDIs and they intended to mix 48, 49, it's a list of 96 or whatever, 48, 49, 50, and 51, but the list also empirically has 52 and 53. That sounds like they're real, that's not so much a coincidence. It sounds like it's like the right next ones in the list and so on. But even if it was like a 3, 4, and 5, which are sort of further away, they're still in the same kit as their others and so on. So, sometimes if it's just for me, I look at the lab or something, right? And I sort of know the lab's history, right? I have a list of all the things I've done for that lab before. Is this one of the sequences I've seen from them before? Something like this, right? So you use sort of information like that to also help judge what could be a real guy. And for dual index guys, you can look at what the mate is, right? So if you're looking at the I1 and you're trying to figure out what's an I1 that's real or not, you can then look at all the I2s he's paired with, right? So if they're all over the place and the design is more like a unique dual or a low density dual, that sounds more like not real, right? But if it's paired up with a very particular guy or a very small set of particular guys, and it hits those, and the mate pair is always a good one first, right? So if you're doing it on a list, the I1 is a perfect match to, the I1 is you know, you're not sure, but you look at the I2, and the I2 he's paired with, you know, you rank order the I2s that he's paired with, and the first I2 is one of the real I2s already in the lane with an exact match, right? That makes it sound like this I1 is more real. But if the I2 hits like nothing in the list, you know, if it's sort of like weird things, or if it's spread along a huge number of user I2s, or if the first I2 is high, you know, a sort of a 2 mismatch away from one of the user ones, then that sounds less real. It sounds more like it's a random thing or something, because you're kind of hitting the user's guides from outside in rather than in out, as you'd expect. Because the default assumption is that yeah, I told you there are cases where the variance beat the expected, but that's sort of the exception. The default assumption is always that the true sequence will sequence the most frequent. So anyway, so that's some hints as to how you can kind of use to evaluate. And yeah, related to this well-known thing is that it definitely the hardest cases I've ever had to deal with. Usually a great simplifying assumption is to find out to define a universe of potential candidates, entire boxes of what the kits they use are and so on. And then you sort of filter the histogram to only those things and things close to that, and sort of get rid of all the noise from all the kind of the really random base call errors and stuff, and just sort of really laser focus on just the guys that are in the kit. And then a lot of times that helps you see much more deeply into lower down in the histogram, because it's not so long now. And you can make decisions using that information. Okay. So now we're going to talk about Demux tolerances. Okay, so BCL, FASTQ2, and BaseBase, they're not as fancy as the web tool stuff I was showing you, where the web tool and so on, index checker, you can give it any set of indices, whatever, with any distances between them. You can even put the same index on there exactly the same more than once if you want. But basically, if all the guys on that list are even getting to 1 mismatch apart, it'll still do distances bigger than that in the rest of the list, right? So it says, oh, number 2 and number 7 are 1 mismatch apart, but then it doesn't give up for the rest of the list. You know, if number 3 and number 9 are 4 mismatches apart, it still does it. And it's very simple, like we were talking about yesterday. It's just basically for each guy, you just compare it to all the other guys, and you find the smallest distance to all the other guys, and then your candidates are exactly those. For the index checker, it just gives you the list of all the ones with the smallest distance. If you're actually doing Demux in that world, you would probably consider guys that are closest to more than 1 at the same time to be Demux fail or ambiguous, and you would not Demux them if it's a unique. If at the minimum distance it's a unique guy that it goes to, that's the pile you would put them in. Now maybe if the distance gets high, you don't really want to accept it, because it's like, oh, it's more likely to be, you know, if it's 5 mismatches away to the nearest expected, probably not. It's not a read you maybe want, because that could just be an index sequence that's just random or whatever, and the sequence is really screwed up and you really have no idea what it is. Just because it happens uniquely be close to 1 doesn't really, by the time you get to that far out, it's not really high confidence anymore, even though it's unique. So yeah, so you know, if you're demuxing, you might have a decision that says like, oh, okay, if the nearest one is unique and the number of mismatches is less than equal to something, then you accept it. But that mismatch distance you allow could be 1, 2, 3, 4, you know, whatever. Whereas the BCL to FASTQ2 is much more limited than what it does. It'll only ever allow 0, 1, or 2 mismatches. And it doesn't allow 1 or 2 in all conditions either. If you want BCL to FASTQ2 to work in 1 mismatch mode, I mean, it'll always work in 0 mismatch mode. That's exact only, it'll always do that. But if you want it to do 1 mismatch tolerance, the sample sheet must have no pair of targets be closer than 3 mismatches apart. So 1 mismatch and 2 mismatch in the target list in the sample sheet means your only option to BCL to FASTQ2 is exact matches. To get 2 mismatches tolerance in BCL to FASTQ2, the target lists in the sample sheet must have minimum distance at least 5. So that's often a limiting parameter. I mean, especially most lane, you know, the generic lane, 1 mismatch is both appropriate and sufficient. And so that's sort of like, okay, so I mean, so the, you know, the sort of the you know, not even knowing anything about a lane, you sort of kind of start with the idea probably it's going to end up with one mismatch. And so, but then, you know, if the user has already intentionally mixed things that are less than 3 mismatches apart, BCL FASTQ2 is not going to do one mismatch tolerance. And so then, well, we'll talk about the games you can then play with that. So these limitations derive because the algorithm that's used inside BCL FASTQ2 is kind of stupid. And it's not even like it was particularly easy to code or whatever. It's kind of stupid for 2 reasons, in that it's inflexible because it has these limitations. But then it also uses crazy resources. The amount of RAM it uses is insane. Essentially, it just pre-computes everything, right? It just sort of pre-computes all possible reads, index reads, in the full error balls and whatever, and just, you know, make some big hash tables or something. And so the RAM it uses is proportional, super linearly proportional to the mismatch tolerance, the length of the indices, and the length of the target list. And so if any of those things get big, then the RAM can go crazy. And the thing that really pushes it bad is large plexity duals. I mean, not large plexity duals, but duals, yeah, basically large plexity duals. Duals that have a lot of distinct I1s and distinct I2s. And you're interested in this full grid stuff for index hopping, which we'll talk about. Because then the number of targets is going to be the product of a distinct number of I1s and the distinct number of I2s. For example, you're going to do a 50-plex unique dual. Well, let's use round numbers, 100-plex unique dual. 100-plex unique dual involves 100 distinct I1s and 100 distinct I2s. The product of those two is 10,000. There are 10,000 combinations of the first and the second. So in this sort of full generality case, the sample sheet's actually going to have 10,000. And that doesn't work too well. That requires terabyte of RAM, just because of kind of the stupid way this thing was written. Whereas you'll see when we do our little R code that actually essentially does the Demux job in the much more general case that the web index checker does, finishes in a minute and basically doesn't use hardly any RAM at all. It's just completely not necessary. It's just, I don't know why that's really like that, but it hasn't changed for years and years and years. And so it doesn't look like it's changing. But it is sort of the only standard tool, and it's sort of at a very kind of beginning, early part of the analytical pipeline, and pretty much everybody uses it. And so there's sort of resistance to using anything else. So we stick with it even so. All right, so because of these red limitations, in particular, if the user targets are close, you're down to exact matches only or something, right? So as I say, because of the effect that actually a lot of kit boxes aren't mutually compatible. If people aren't pre-planning their mixes with index checker or something before they start choosing what indices they're going to use or what they're going to mix together, you get these cases where the intended target list has 1 or 2 mismatches. And that pushes you into the 0 mismatch world in BCL to FASTQ2. And we've already seen from yesterday that 0 exact only mismatches can really cost you sometimes in recovery. Maybe the lane as an average is okay, but that doesn't mean individual samples are okay, right? So we had that guy yesterday that was basically 20 million recovery with 1 mismatch, but only 60 million recovery with 0 mismatch, because there's a 1 mismatch variant that's like 4 million. A single 1 mismatch variant is like 4 million. That was the situation yesterday with the number 19. And so you get situations like that. And so then you start playing games with the sample sheet. You basically got this fixed combination of sample sheet and BCL to FASTQ2. That's your universe that you can play with. And so what can you do in that universe to try to recover from situations like this? So in that case, one thing you could do is you could add an extra target to the list. Right? You're already in the exact matches only row. So now you can feel free to add as many lines to the sample sheet as you want, because it's not going to trigger any further lowering of the Demux tolerance. You're already at 0, the minimum only. So you can take this variant mode, this 4 million variant mode that we had, and just add it as another target, right? And you're going to get it in a separate set of output files, but that's okay. You can manually just combine that pile with the number 19 canonical sequence after BCL to FASTQ2 is done. And so you can get your 20 million reads out. You just got to do a little more work. But you can basically claw back your missing variant that's valuable because of the representation. The other way you can kind of try to skirt around that game is that, well, okay, maybe the user has a 2 mismatch conflict inside there, just for sake of argument. I mean, sometimes we get cases where there's like 20 pairs of two mismatched conflicts, but let's just say it's an easy case where among all the user targets, there's just one pair that has two mismatched conflicts. Even better, maybe say one of them is high rep and one of them is low rep. So what you can do is you can actually say, take the low rep guy, leave the high rep guy alone. Take the low rep guy, and you're going to intentionally change his target to be one mismatch away. One mismatch away in such a way that after you make that change, you remove the two mismatch conflict because you turn it into three mismatches. Okay. So you look at the conflict margin, and then you're aiming to choose some alternate, not even necessarily a high representation in the empirical histogram, alternate guy for this low rep guy that's conflicting. But you basically push him in a direction away from the guy here that's causing the two mismatch conflict. By pushing that away, you increase the minimum distance in the whole lane to three mismatches. You enable BCL to FASTQ2 to now use one mismatch tolerance. And now the one mismatch tolerance will still capture the guy that you just lied about what his real target is, because your real target is one mismatch away from his real target. And so so it's basically conflict is here, push this guy away to increase the distance here. Now you can do one mismatch tolerance. This grows a ball, this grows a ball, but the original guy that you pushed away from here is now inside the ball down. And so this is what I call intentionally targeting off center. And you can even play games with the particular variant that you push this one to off center so that, well, first of all, you have to make sure you don't push this one closer to somebody else. I mean, it's a little, it's some finesse required, and sometimes it's tricky. And what's really tricky is when there's like 10 conflicting two mismatch pairs, and then sort of simultaneously finding a solution that pushes everybody away in just the right way that kind of gets you back to three mismatches. But so you can kind of basically, there are games you can play with if you're limited to this world of BCL of sample sheets and BCL FASTQ. There are games you can play to sort of deal with various situations. Okay. So we're now going to talk about, well, okay, so that's the idea. So that, that's the framework that this mismatch tolerance stuff exists in. But now we want to sort of make intelligent decisions about whether we have to, is zero mismatch sufficient? Basically, because Demux is always this battle between recovery and mis-Demux, we sort of know, well, recovery is generally easy to measure. So that's the one we generally concentrate on in terms of making a decision. Recovery is very easy to do. You do the Demux and you see how much you get out, right? Or you basically simulate the process and see how much you get out. You don't actually have to submit the reason the files and so on. As long as you count the number that would go if you were to do it. So high recovery is good in the absolute, all other things being equal, higher recovery is better. But of course, how do you get higher recovery? It's generally by allowing more tolerance. What does more tolerance mean? It means you're taking sequences further away from the intended targets and putting them into files. Well, eventually we know that if you go far enough away, that's not going to be right? I mean, intuitively, the higher the Demux tolerance, the more likely the mis-Demux will be higher. And mis-Demux is bad, right? So unfortunately, it's generally hard to directly measure mis-Demux. That requires something like we talked about yesterday, where you have something like an amplicon library or something where you sort of know that the genomic region is sort of already the identifier. And so you can cross-check that against the sample ID that Demux has in the index. But most of the time, you're not in a situation like that. You don't really have direct visibility of mis-Demux. And so you sort of just know that, okay, higher Demux tolerance that's pushing me into the mis-Demux direction. And you go too far out there, like 3, 4, 5 mismatches. Well, maybe the 3 is something about it. But by the time you feel like 5 mismatches, you're probably the incremental benefit, that marginal benefit you're pushing out, probably is going to be a very small recovery benefit. Because probably almost all the guys you're throwing in there now are bad. So you sort of, you're thinking more like 0 and 2 or something. But you'd rather basically say that because mis-Demux is bad, it's like mixing samples. It's like opening up all of your tubes, strengthening computing thing, to more, whatever extent. But people wouldn't tolerate you even just, dipping a pipette tip in one and then the other, which is going to transfer a very small fraction of the volume, but it's going to be contaminated. So the basic idea is, if there's big gains in recoverability in recovery, that don't push the tolerance very high. Like if there's very, if you're going to 0 mismatch to 1 mismatch, you get a big gain in recoverability. Probably you're going to want that big gain in recoverability. But and maybe 1 mismatch, 2 mismatch, you got to then judge kind of like, okay, is that gain in recovery worth it? But it would take kind of a special instance for like you to go from like 3 mismatch tolerance to 1 mismatch tolerance. Something would have to be amazing and having a recovery or something. Kind of so the general idea is that sort of each step up in tolerance is got to be judged against the amount of recovery benefit. The recovery side of the equation, you're going to be able to get real numbers on. This Demux side of the equation, you're not really going to have direct evidence. So then we just have to kind of, basically our focus then just depends on kind of looking at how the recovery changes as change the mismatch tolerance. And then based on that and sort of just general knowledge about what kind of mismatch tolerances is what kind of mismatch, then we make our decision. And so, okay, so not only do we need to choose the tolerance, but this analysis procedure we're going to do is also going to, for the cases that, like I say, maybe you're in this world where like you're forced to 0 mismatch Demux in these little FASTQ2. How do I find which samples need variance added to kind of recover their guys, or the samples that need to have the gain of off-center play? So this analysis will also help you with that. So this analysis is sort of intelligent. Let's try to choose Demux tolerance rationally. Let's find out if the lane has cases, identify lanes that have cases that need remediation, and then also what is the remediation going to be, the details of it. This is what this analysis is going to do. And this is going to occur in R. So I'm going to start R on my local machine. And can I make this bigger? Oh, does that work? I guess that works. I don't know. Not big enough, maybe a little more. Okay, so first, we're just going to have a little helper function here. And the point of this function is just to help make names like this. So this just puts 0 padding in, so all the names get the same length, so that if things get sorted as strings or as numbers, it's not going to matter. So like if I had asked it for like 5 to 100, you'll see that it now uses 3 digits because you need 3 digits to cover that. So that's just a little helper function that just kind of helps us make nice names for things. And now we're going to start, we got to read the data that we need for R. What's R going to need? R is going to need the empirical index histogram, and R is going to need the list of what we chose as the empirically present canonical indices. Those two files, which we have as 2 files in Hoffman 2 right now. Right, so there's the histogram file, and there is the empirical canons we chose. Right? So here's a little magical read table syntax. The interesting part for you guys is probably going to be this part, which I basically call the poor man's network file system. But if you've gotten Hoffman 2 with a point where you have RSA, private key, public key, a passwordless login, so you'll notice that here, if I do my SSH into Hoffman 2, I do not get asked a password. Right? That's because my machine has a private key, and on the Hoffman side, the public key for it is in a special, I think it's in your SSH directory authorized keys, right? So these are the public keys that anybody that can prove that they have the private key paired to that public key is allowed to log in as me without password interaction. So my laptop has a private key that authenticates it to Hoffman as an authorized key. So that allows me to log into Hoffman without a password, which is quite nice because it means you can script SSH at that point. So basically what we're doing here is we're SSHing into Hoffman 2 or the DTN data transfer node, just to keep off the login nodes. And we're running a command as if we were typed into a command line on Hoffman 2. And the command is cat, as if you would just print out a file on standard output. And here's the Hoffman path to it. And we put that in a R pipe so that R basically runs this command on my local computer. The paste 0 is just because this command is very long and I didn't want to split it across 2 lines. It's a little tricky, the rules for R and splitting new lines inside the middle of strings. This is all just one long string. The paste 0 just puts them together with nothing between them. It's just direct concatenation. Oh, that's not R. There we go. So that just makes a long string all with the pieces there. And so basically this is for small, you don't want to do this for a gigabyte file, but for small files, this is very convenient. Because basically it means that this is going to dynamically pull the contents of this file into my read table, and I don't have to transfer this file to my local machine first. Right? It's basically a way to directly make files inside Hawk and directly available to your R. So that's kind of cool. Oops, there's some fat fingers on the keyboard there. All right, so let's paste that into R. Okay, and my firewall is saying R is trying to talk to the outside world. But there you go. Okay, so that is a 25697 by 2 data frame that has 2 columns, MER and tally. It is our histogram. And it also has row names that just serialize the index histogram. It's always nice in R if you kind of have row and column names and everything, and they kind of just magically come along with you. And so the H reminds us that these rows are histogram rows, and they're just serialized by the rank order of representation. So that loads up the histogram, and now let's suck in the list of same thing in the other file, but it's a 1-column file. This is the our list of 21 canons that we chose, right? Which I'll call C01 to C21. Just the C to remind us this is our empirical canon entry. Okay, so that's the data we need to compute with. Now we got to actually do some computation. We're going to be using some libraries here. StringDist will be the library that computes the mismatch distance for us. Not that that's particularly hard to do. That's called Hamming distance, just counting mismatches. Basically, walk along the 2 strings and count the number of discrete positions. StringDist, though, does do the indel stuff, which is a little harder. And of course, the tidyverse stuff is always very, very handy. If you're not knowing about the tidyverse in R, you really should get into that because it's really, really super helpful. So here I'm using dplyr and tidyr, part of the tidyverse, and that is really good stuff. So we get our libraries going. Okay, and so the first thing we're going to do is the actual, basically the demux, which is the procedure I was telling you just a second ago, which is for every entry in the histogram, that's an index read that we got. It's really, the histogram nicely collapses all the copies of that read all over, force them to one entry. So that, like, some of those guys would be 30 million times, but that saves us from recomputing the same result 30 million times, because we're only going to get one histogram. And we just have a little column there that says, oh, this is the entry, it's 30 million times. So that'll be a great computational time save. We're just not going to waste recomputing the distance business for all the copies, except for the ones we distinct back. But it's the procedure I was talking about a second ago, right? For every guy that you saw as an index, we compare him to all the canonical, find the minimum distance, and then is that minimum distance realized, but it's one guy or multiple guys? If it's multiple guys, you must fail. If it's a single guy, well, that's the pile to go. Okay, and if we have 21 targets, and it's convenient to just to keep the numbering consistent, we will use pile 1 to 21 to mean canon index 121, and we use pile 22, 1 past the end, to be demux. So that way we can have all the piles just numbered, basically the same as the canons list, and we'll just have one. I think BCL fast use numbers in a sample 0 rather than the bottom, but in ours, R not comes from 1. Okay, so we got to run it. Okay, so I mean, so here's the code basically. This just adds 2 new columns that'll have the information, the minimum distance, and which guy achieves the minimum distance, the demux pile, and we'll just fill them with -1s to start. And there's going to be a little progress bar so that we kind of see how fast this is running. And then we just loop over every row in the histogram. And for each row, we pull out the observed read sequence. We call string mismatch from StringDist library, which computes the distance of that to all of our canonical guys, gives us a little vector back to all the distances. We find out what the minimum distance is, and then we find out at which indices that is achieved. And if there is more than 1, then demux fail, which is the number of canons plus 1. Otherwise, there's only one of them that achieved the minimum distance, and that's the pile it goes into. And then we record the information we just computed into our big, the 2 new columns that we've been doing. And then we update our progress bar to the finished one. Okay, so and at the very end, you have to remember to close your progress bar. Okay, so here we go. We will paste that into R, and this is essentially doing the entire Demux. It's just not bothering to gather the actual read sequences and compose the output files or something, but we're basically deciding where every lane, every read in the whole, every well in the whole flow cell would go in a Demux analysis. The flexible Demux analysis, it's completely generalized. There's no Demux tolerance yet. This is sort of the arbitrary tolerance analysis. Okay, so you can see it doesn't take very long. Okay, let's look and see what we got out here now. I actually put the result in the same histogram we started with, right? So that our data frame just grew by 2 new columns, right? So there. So no surprise, we know that the beginning of the list is the canon guide, right? So actually, I think we numbered the canon in the order of 2 anyway. So minimum distance from the beginning is all 0, exact matches to canon 1, 2, 3, 4, 5, 6, and so on. Right? Here's the bottom of the histogram, which is going to be stuff that you can see. Now the minimum distances are 3 and 4s, and whatever. I mean, we're not going to probably adopt these, but there's these at least are all. Well, 22 needs Demux stuff. Right? So there's 1 to 21 in the guys and Demux stuff. 22 is the Demux stuff, and so yeah, these are going to be rich Demux stuff. So like this guy. At 4 mismatches has multiple guys for that distance. Although this guy has 3 mismatches away. But okay. So anyway, but this is basically that's the core information we need to keep going here. That's essentially the entire an arbitrary threshold Demux operation, analysis there. Let's let me show you just a little more rows of the top there. I guess let's do maybe 30 rows. Oh, that was a good choice. Just the window height. So you can see there that basically it's if you remember it was like solid green, then skip 1 and then 1 more green. That was like the order of the canons versus the histogram. So that's the first 20, which are actually the expected guys. There's the 14 million number 19 expected sequence. There's the 6 million number 19 1 mismatch away sequence. Here is the phi x canonical sequence, number 21. And after that point, there can be no more zeros after this point because we've now seen all of our 21 guys on our canonical target list. Everybody that's less has to be at least 1 mismatch away. And then, it turns out the next one is 1 mismatch to number 16, then 1 to number 5, 1 to number 19, 1 to 5, 2 to number 19, and so on. So anyway, so you see there. That's a very, very, very nice matrix. The data frame has got 2 very nice columns in it. Here's kind of a little stupid, this isn't really a serious plot, but just, it's kind of cool too. But so that is just, as you go along the rank order of the histogram, which is the x-axis, the y-axis is the minimum distance. So this just shows you the general trend. This is stupid because really, I need to sort of do some kind of 2D thing here and show you the distribution, right? It's too many dots on top of each other to really tell what the density is. You're not supposed to make scatter, dot plots like this, and the dots get so much because basically everybody overlaps. So you have no idea this could be 10 times the density of that, but you don't know because once every pixel on the screen is covered, you can't tell anymore what the density is. So that's why I said this is a stupid number. Really, if you really wanted to show this, you got to make sure that you're showing the real difference. But you kind of see that, if the Demux method, the ones and the ones peter out, and pipe down the range. And here is that distance. This is now the same plot, but the other column. This is the 1 to 21 or 22 equals Demux fail. The guy that is hitting, that minimum distance is achieved at. Well, it's basically, you're hitting all targets all the way through. Okay. Now, we want to make a summary of this thing, right? Once, we're really interested in what the recovery would be in the Demux files. with various tolerances. To do that, we aren't when we're interested in say less than equal to 1 mismatch tolerance, we don't care what the particular variants are or sequences anymore, right? We just want to know how many guys go to number 19 if you allow 1 mismatch, not like what all the 10,000 little sequences are that are going in that file. So we need to do some kind of summarization now where we keep track of the target, the pile it's going into, and how many mismatches it took. But we no longer want to care about the sequence, right? So we want to drop sequence from the equation. And this is where defiler and filer are like pillars in terms of like readability, efficiency, and so on. So you kind of read this as a little pipeline. Start with data frame HI1, and then you're going to apply these transformative steps one at a time. The first two, let me skip the first two, but basically, because we could have, don't worry about the first 2 rows for now. We'll talk about them at the end. But basically, the first step is to group by the column dist mn min. I group by 2 columns. So the major order is which pile it goes into. So major group is which pile it goes into. Minor group is how many mismatches away into that pile. That's the 2 things we want to organize the result by, basically. Then what that group by does is now breaks the input table into subsets of rows that share those 2 values. So if 2 rows share the same pile they go into and the same mismatch distance, they're grouped together now by that group by. And so now the table is really now a table not of rows, but tables of groups of rows. The next thing says summarize. And what summarize does is takes each group and collapses it in some way. And we're saying that in the collapsing, you're going to make a new column called tally. And the new column tally is equal to the sum of the old column tally entries in the group. So basically, we're just saying the summarization is take all the guys in the group, add up their tallies, right? And that's the size of the Demux file with that many mismatches to that guy. At that point, the grouping is no longer, we've done the grouping, we now ungroup. And this arrange is to guarantee sorted order. So this arrange resorts the rows so that they're, it's sort of unclear, I guess, in the documentation whether the group by summarize is going to leave things in the right order or not. So this, at least the arrange just makes it explicit. This is an explicit sort that says that reorder the rows majorly by the Demux pile, and then if there's ties, by increasing distance. Okay, so that's now the order we've got the rows in. And then there's this, so as far all this stuff is part of dplyr. This pivot wider is part of tidyr. The pivot wider is now how we go from sort of like this 1D representation to a 2D matrix, okay, pivot wider. And so what we want to do is, right now the rows are based on the combination of pile and distance. We want to rearrange that so that the rows are pile and the columns are distance. And the entry in the middle is the tally. So this is this pivot wider. And so we're pivoting wider where the rows that we want to keep the organization by is, the rows that we want to keep the organization by are the pile. So that's called the ID calls. What we want to become the new columns is the mismatch distance. That's the names from. Then the values in the cells are going to be the tally. So that's the values from. And then if there's any holes in that table, because now you're making a full 2D matrix and you may not have entries in the long row table that really cover all those entries. If they're missing, it just means for us they're zeros, right? So it just means that there wasn't a combination of that guy at that distance, but some other guy might have had that distance as a mismatch, whatever. So this just says that if there are any holes as you form that matrix, put a 0 in the holes. And now I can also explain what the first 2 rows do. They just added some more rows to the original table with 0 tallies. They just guarantee that every target is in there and every distance is in there. So whatever the maximum distance is 6, we want to make sure we have a column for 0, 1, 2, 3, 4, 5, and 6, even if somehow there was a column of all zeros. So, because I want the final matrix to be, rows 1 to 22 for all the targets in order, then Demux fail. And I want the columns to go 0, this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? So basically, this values fill stuff, and these first 2 rows just guarantee that the matrix we produce is completely full in that sense. Okay, and then that'll leave the column, it'll leave the Demux pile number as an extra column, but it's now redundant with the row number, basically. And so this select minus means delete this column. It's no longer. Then it's a data frame at that point, or maybe a tibble. And we don't want it as that fancy. We're just turning it into a regular R matrix at that point. And then we'll put nice row and column names on it. Okay, so this is really cool. This kind of how compactly and efficiently this is done here. And now we have this matrix. So the row names are, of course, our 21 targets, and the last one is the columns are now the mismatch distance 0, 1, 2, 3, 4, 5, 6 here. 6 because that was the high. Demux has an entry out there. Nobody else did. You see now some of the zeros that got put in there. And then the entry tells you how many guys are going. So if you wanted to do exacts only Demux, that first column, that's the size of your recovery. If you wanted to do less than or equal, if you wanted 1 Demux tolerance, meaning you would accept exact matches and 1 mismatches, because these are not cumulative, right? This is guys at 1 distance. So if you want to say less than or equal to 1, which is what you mean when you say tolerance, then you add this number, and that's how they compile for 18. Okay. So you can now see this is a very information-rich matrix for the kinds of questions that you want to answer. Okay, so let's get some of those numbers out, right? Okay, so we can already tell, I mean, we computed this before. Oops, that's not our, maybe I should just hide that guy for now. So my command tab to switch windows doesn't keep finding the wrong one. That's the number of PF1 wells in lane. It's simply going to be every well in the whole lane is in exactly 1 square. So we can just add up the table to recover the number of PF1 wells. And then I was mentioning these are not cumulative, right? So if you wanted to do less than or equal to M mismatch tolerance, you got to add up the first M, M plus 1 column. Right? So we need to, if you want to compute the recovery with less than or equal to X tolerance, we need to do cumulative on the row. So let's do that transformation. So, and then let's express it as a percent of PF1s. All right. So we do cumulative sums of each row, and then we just scale by 100 divided by 1. So it's in percents now. Percentages of PF1 wells. So there it is. So this is now recovery for the whole. I did the column sums, then the cumulative sums. So this is the recovery for the whole lane. Right? So this is the lane average time. So with 0 mismatch tolerance, exact matches only, you recover 96% of 96% of PF1s go in a file. That's not Demux fail. So you see here that I use the rows, only the rows that correspond to the guys that we targeted. If I didn't run, if I just left a blank here in this comma, or if I put 21 here, 22. If I put 22 here, then we would have been including Demux fail file. But we don't want to include this fail. This is basically all but the last row. So this is all but the last row, meaning all the actual targets, not Demux fail. Not Demux fail. The call sums forgets about who's contributing, takes sum of everybody, and then the cumulative stuff is the cumulative things, and then so this is exact match is only 96.3% of the lane goes file if it's not fail, and one mismatch 99% of the lane, and then so on. So we could, you can visualize that if you want. There you go. So that's basically recovery of the whole lane versus Demux tolerance. And you can see here, well, index is kind of stupid because it's misnumbered, right? That first one is 0 or whatever. Did I get that better when I made my plots here? Yes, I did. So that already had the right names on it. That's not, I guess that's not necessary. But then in this plot, we do the we explicitly specify the x values that they're numbered right, start from 0 and not 1. So there we go. So that's Demux tolerance by percent of lane goes in non-fail. And so you can see here the big jump from 0 to 1, and then it kind of plateaus. And so from this view, we're already thinking, well, you know, if you know, I wouldn't probably go past 1, right? So most of the gain and recovery is already 1. So although 0 isn't really that bad either, right? 0 is already at 1.6% or something. So that's not too bad. Doesn't sound too bad. Okay, but then, you know, we can do this analysis finer than that, right? Because we have the information per sample. So let's look at per sample. So now we're thinking, oh, and mismatch. Okay, so let me just run these lines and then we'll explain them. Well, okay, so here what are we doing? Temp is the matrix, but drop the last row. And that's to get rid of Demux fail, right? So temp is just the same, is the matrix without the last row. So that now temp is the everything but Demux fail. This is column 2 of temp, which is the recovery at exactly 1 mismatch. The denominator is column 1 plus column 2 of temp, which is the recovery with less than or equal to 1 mismatch. And then the 100 is percent. So this is per sample, percent of recovery using less than or equal to 1 mismatch that requires the 1 mismatch. That's what this is. And so there. And what do we see? Well, first of all, notice that the y-axis is 0 to 30-something%. Obviously, sample number 19, which is of course the one it's going to be from what we've seen before. Sample number 19 has 30-something% of its recovery at less than or equal to 1 mismatch requiring 1 mismatch. He's clearly the guy that's needs. So this basically tells us the 2 plots together are telling us basically you want 1. You know, there are these other 3 guys that are getting 4% benefit. That's not. I wouldn't throw that away either. But the real, you know, it's that guy. This guy, the reason why you don't want to not use 1%. This way. So, but we don't have that flexibility with these other tests. It's a full lane single knob, 0, 1, 2. With index checker, we can put in our list of targets and find out. So, oh, I hid that terminal window. Here is our list of the 20 targets, and well, I don't have a Firefox yet. How did you get rid of that? So I'll place those in. And the minimum distance among our 21 empirical targets is 3. And that means that for BCL to FASTQ2, our choices are going to be 0 mismatch or 1 mismatch. That's our only option. We can't do 2. That would require 5. But 1 is an option because the minimum distance here is 3. But it's a whole lane thing, right? So it's like we can do the whole lane at 0. We can do the whole lane. And right now it's going to be 1. Okay. Now suppose because maybe something else that was in lane or something or whatever reason, that minimum distance was 2 or 1. Well, now your only option to BCL to FASTQ2 is 0 mismatch. Now you're thinking about but now you see this plot, right? And you say, I don't really like that because this guy's going to be first. I don't want to lose 30-something%. So what can I do? Well, then you start playing the game. It's like, am I going to target off center? Am I going to add some variant? What am I going to do? But how can I find out that we know number 19 is bad to worry about? We don't know which sequences we target. So how can we do that? I mean, in this case, we know because it wasn't complicated and it was a complicated system. But you know, we've got all the data in R at this point. So how can we investigate, say, number 19 situation a little more? Okay, so that is C19's equal to 0 recovery and equals to 1 recovery. Adding those two up, we get C19's less than or equal to 1 recovery. So that's, if you did real one mismatch demux for C19, that's how many guys would get. Now let's look at some other things. Okay, first of all, how many, in the arbitrary demux case, how many distinct sequences go into C19's pile? It's actually 543. Okay, suppose you only look at the ones for mismatch distance less than or equal to 1. How many distinct variants do you need to cover less than or equal to 1 mismatch for 19? 28. So if you really wanted to replace less than or equal to 1 mismatch exactly with, say, the add variant approach, you have to add 27 more targets, because that's how many guys are in the actual observed sequences are going into the one less than or equal to 1 demux file, not 28, because one of those is the exact guy, which is already in. So it's 27 additions, you'd have to add 27 guys. Well, let's actually look at them and maybe make a decision here. So yeah, 4 is slide. So this is the arbitrary analysis for 19. All right, I'm only asking for the target for 19. This is the subset of our histogram where the best, where the pilot goes to. So you can see that, okay, so yeah, okay, 14 million exact match, 6 million this guy. Okay, so that's a lot of it. Now it's fallen off. This is another one, 460K, 1 mismatch, and then there's this guy at 2 mismatches away, 36K, and so on. Anyway, you can see that, and then maybe you want to see just restricted to the just show me other ones where it's less than or equal to 1 mismatch. That should be the list of 28, right? So then I can also do, let's also constrain to where that's less than 1. That should be 28 rows. So that's the full less than or equal to 1 demux. What goes into the but you can see here, it's basically very much in that first variant. And so if you're only going to add 1 variant, this is the guy you would add. And how much, how much are you recovering then of the full thing here, right? So let me save that. So that's our less than or equal to 1 mismatch total answer for number 19. That is then the total number that you would get that way. And then how many, if you just took the exact match guy and then you know what? Stop doing that. If you took the exact match guy plus this guy, that would be 97% of what's possible. So by adding a single variant murder, you get 97% of the benefit of a true less than equal to 1. You would add 1 more row to your sample sheet with this variant, mark it's number 19 variant 101. When BCL cascade is done, you'll have 2 more, more files that are tagged that you got to merge that with the 19 variant. Your mitigation for this recovery loss if you're forced into exact match only. And for example, one way that could happen is just looking around. I was like, suppose somebody decided to do a spike in this lane. One of your lab members comes to you and say, "Oh, you're doing some sequencing. I got the sample. You run it for me, just really low concentration. I just want to." And so he hands it to you and you mix it in. But it happens to be Illumina UDI 80. Which is this sequence, and it turns out that's only 1 mismatch away from your number 15. But it's actually greater than or equal to 3 mismatches away from everybody else, right? So if I just take this this, I think I still have index checker still open here. So there, I'll add it at the bottom, and there's a 1 here, right? So it's greater than or equal to 3 to everybody except number 15, where it's a single. Well, now if you want to submit the sample sheet to BCL to FASTQ2, you're forced to the exact matches only world because of this stupid little piddling spike in library like that. Okay. How are we doing? That's an hour. Maybe a good point for a break. Sip the water here and see if there's any questions. How's our Zoom attendees doing? The chat window's been completely empty here. You only have to do the ones that you're worried about, right? So obviously, if this lane was possible to do at one mismatch tolerance and be so FASTQ 2, that will already capture this guy, this variant for the number 19. No need to add anything. It's and in this case, you would also not really have to worry too much about the other guys. Unless you want to make, if you were to go to the next level, you should look at these two, right? That's really the next kind of level, and they're 4%. But it's diminishing benefits, right? But this, at least what this analysis allows you to do is make intelligent decisions. Right? Let's figure out what the situation is, evaluate what are the cases you want to address, and then how would you address it. All that information. Okay, so basically this whole, basically a full day, it's like started in the middle of day one, and now it's, well, whatever, it's a little less than a full day, but we've been building up to this point for a while now. But we're ready to do the Demux run of these subtests. We are very confident about our samples. Right? We checked it against empirical. We know it's going to do a good job. The only thing left to do is actually execute our plan at this point. So the command line is basically the same thing as the non-Demux run with just a few changes. So because the index reads will be used in this stage and we won't really need them after this point, we'll just not generate the I1 files anymore. So we'll drop that option. The sample sheet in dev null now has to be sample sheet the real thing, right? So if we got to point it at the file, it's the actual sample sheet. And we already talked about the adapter issue there in terms of metadata and doing adapter stuff in downstream read prep tools rather than at Demux BCL to FASTQ raw run folder to FASTQ conversion stage. What's the next thing? Okay, barcode mismatches. We now understand that parameter and we've done an intelligent choice here. That's going to be 1 for this case. And the use basis mask we don't have to change it in this case. Y1N50, I8, Y1N50. That I8 forms the sequence that BCL to FASTQ 2 will use to make the Demux decisions. So if I, for some reason, wanted to throw away the last base of the index and just use I7 with the last base gone, I would say I7 N1. Or if I want to throw in the first base, I could say N1 I7. If I had a UMI around, then you definitely want to drop it because that is a randomized sequence that isn't supposed to control which pile it goes into. That's what the other bases in the index go for. So if you had, for example, a 24 base index read, I1 say, where the first 8 bases was the sample ID, and then the back 16 bases of the UMI, we would say I8 and 16. All right, so you get how that goes. And we just have to name our output directories different because we don't want to collide on the non-Demux analysis we already did. But that's it. Okay, so because I already have a version there ready to go, because we're not going to want to wait the half hour this takes to run or whatever, let me just rename the file, rename the outputs. They're not going to collide on the one that we've already got. And just to prove that that command starts, we'll paste it in. And there it goes. And you can see that now we're getting all these additional FASTQ outputs that we didn't get before because now we're separating into piles. Okay, so we're going to let that go. Let me get on Hoffman again, so we can look at the version that's already done while that runs. Okay, so the output that I already had ready is this directory here. There's our live one down here working away. And so what does that look like? Well, now you still have the Demux fail pile, but it's a lot smaller than it used to be. Right. So if I look at go up one level and then look at the non-Demux guy, these files are much bigger than this file. Right? Because this is a non-Demux run, all the reads one Demux file. Now we've only getting the stuff that doesn't match at one mismatch to our target list. So these are much smaller. Where has all the reads gone? Well, they've gone into these directories, which are basically triggered by the project names in the sample sheet. And so in the project one directory, we have, that's not very nice. There we go. We now have R1 and R2 files because we have SE and PE is paired in main reads here. We have a pair of output files for every sample target in the sample sheet. So, and then the project twos are in their directory. Oh, yeah, I never changed into the project one. There was no need to back up another level. So here we go. There's the project twos. And then we put phi-x because it's not really belonging to either project. It's part of the mix of the lane that's in its own directory there. And the file names are basically exactly your sample name, then underscore S, and then a number, which is the serial number, just the row number essentially in your sample sheet, with the Demux fail getting a 0. And then we talked about the LO1, R1, 001. That's the lane read number within either the main ends or the index end. There's no index ends anymore here. So it's just the main ends, main end 1, main end 2, and then part 1 of 1. They're not going to be subdivided into smaller files. And then the read names inside are they're almost exactly the same as the read names were before, but you do get the index sequence in there. So if I look at one of these FASTQ's outputs, here are the read names, and these are cut down to 1 base, of course. But instead, we used to have a 0 here. If you remember, the non-Demux file was always a 0. But now we actually have the index read sequence. So this is essentially the index reads are still here. Well, the index read ACGTN discrete base calls are still here. We do have the quality scores aren't here anymore. Why they didn't throw that into, I don't know. But it's too late now. This format is so widely read by so many tools, we'll never change it. But that's the only thing we've lost by not admitting the I1 file. We lost the per base Q scores of the index read. But the ACGTN sequences are here. Maybe it doesn't look like that right now. Maybe you think this is just the canonical sequence that's in the sample sheet. So that's because we haven't seen a variation yet. But if we de-unzip that 4-line to 1-line trick, and then first line has the sample names in it. There you can see a little more, and you start to see here. Here's some ones with an N. Here, let me turn on the highlighting. So this is the canonical sequence. Right, so yeah, can we find one that has a base mismatch? Yes, we can. So there's one with a single base mismatch. So those are the index reads, not the canonical sequence. Okay. One of the numbers you want, I mean, we already kind of know from our R analysis what the recovery should be, but you probably want just the actual recovery out of B-cell FASTQ2. That is in this horrible kind of XML file here. So here's the output directory of B-cell FASTQ, and then if you look in stats, it's the multi-stats.xml. This is essentially the information of how many reads are in each file, but it's in XML. So I give you a little XSLT transformation sheet. This is just a little XSLT. It's also a horrible format, but whatever. XML to do XML. It's essentially a little tiny program that tells you how to reformat this thing into something that you'd actually want to use. And the way you use it is with this XSLT proc that you feed it that transformation program, the input XML, and the output file that you want to write from that. And that has produced this Demux stats txt here, which has the same information just organized in a much more nice way. which is simply as a text file, where yeah. This is all the information in that XML file, not all of which you care too much about, but I kept all the columns that are in that thing. So flow cell ID, project name, sample name, the sample sheet barcode for that guy, the lane number, and the total size of the Demux file that BCL FastQ produced. Then the information about how many are at each distance. This many in the output file, this many 0 matches away, this many 1 mismatch away. Okay. Kind of like the table we made in R before we did the cumulative sum stuff. So that's got all the information. You may want to summarize that even further. Like mostly you just want to know like sample and total size of output. So here's a little, we'll just do a little pipeline there. We'll just cut out the 2 columns, column 3 and 6, get rid of the labels, the row labels at the top, and sort it into descending order by the total representation. And so it gives a nice little summary of these are now the counts out of BCL to FastQ2. Okay, so that's basically sample name, total number of entries in that FastQ file for that guy. And undetermined is the Demux and phi is there. So that's at this point you pass to downstream, right? So now you do your standard reprep, whatever your downstream analysis is, RNCs, whatever, alignments, whatever. But this is the total picture of how you would take a raw run folder to Demux Chapter. Okay. All right. So a couple summary numbers you probably want to compute at this point. Recall that the total number of PF1s on this flow cell. Not on this flow cell. Yes, on this flow cell. The total number of PF1s was 496 million. And so Demux fail, which is 4.8 million here, just divide it. It's about 1%. So about 1% Demux fail here. That's pretty good. We've 99% of the wells in the lane that aren't empty, right? Obviously those are dead. But 99% of the wells that got filled, we put in a file, right? That isn't Demux. So that sounds pretty good. And there can't be anything big left, right? It's just, there's not anything to discover really left in this line. And phi x was 3.5 million, so you divide that out, and that's like 0.7%, and that's not really too far away from the nominal 1% spike. So that seems in line. And of course, the balance then would be 98%. So about 98% of PF1s became put into user piles. So that's sort of the efficiency of, apart from the question of percent PF1, that's the efficiency of the Demux process, basically, and the balance between user and files. These are the histograms over about 200 runs for those 3 metrics. So the Demux fail. Now this is after I do my empirical stuff. So if you actually do this on the base numbers or something, the distribution shifts to the right. So basically what I'm saying here is that when you do the empirical process, this is what the typical Demux fail looks like. And it's basically concentrated around 2% with the common variation being like 1 to 2%. Meaning that if you haven't explained about 97% or more of the reads, maybe you should go you see there's this spread out here. Some of these are cases where sort of like you can't really get detailed effects if you really use tolerances you want. Only remediating with all variants as possible. And then once in a while you get out here, there's lanes where we really can't explain it. But you can set the meets all down here, 1 to 3%. The phi x percentage, we aim for 1%. It's like right here. But for some lanes, we actually intentionally use the slightly more, like for the day 3, we'll talk a little bit about phi x. But the industry uses the lane gardener for lanes where the main reads are unbalanced in composition, let's say by sulfide. The T percentage is very high, the C percentage is very low. In most we would sometimes spike in large enough of phi x to bring the main read closer to ACT so that the base colors would go nuts and script the main reads. So some of these are intentional, and then sometimes just fives like out convincing stuff incredibly. So there are things like insert length and so on, and some of the efficiency that things happen. If your insert lengths are really out of whack for what the instrument wants, then you put in sort of like a library that it does like, then that'll help. So sometimes the fives goes nuts. It's because the user library is not, the machine doesn't like it. It's not putting the machine in the sort of regime it wants to be operating in. The other number was the percent of the PF1s that land in the user file. And it's sort of related to 100% minus this. Not quite that, because you need, for duals, we're going to talk about index hopping now. And that's the other number that's missing out in this picture right now. So there can be another pile, which is the stuff that isn't paired the way it should be. But a module of that, you can see it's basically like 97%. If you're down in here, then that's more. So some of this is because there's empirical extras, maybe something called G, poly A, and so on. And there's lots of reads going in those piles and not into what you're expecting. So this goes down here kind of for reasons like that. Okay. We already looked at the run folder and the files that we get out. And we already looked at the reads and so on. So there. So that's it. That's the complete. This basically, that's the complete story on single indexing. I mean, I haven't really shown you all the crazy ways that things can go wrong and all the zoology of all the problems. We'll go over that tomorrow, I guess. Well, the rest of today, basically, the goal is to talk about dual indexing. So dual indexing. I mean, we talked the first day about read formats, right? So you already know that there's I1s and I2s. You can do an I2 if you want. And why would you do it? Well, I think the original motivation was when index reads were younger, they couldn't be very long, like 6 mers. So, and with 6 mers, if you want to have any minimum distance between them at all, you're going to be limited in how many you can have. Right? You're not going to have 1,000 6 mers at minimum distance below each other. It's just not possible mathematically common for it. There's some work we have to do to actually finish solve that. It's a mathematical common for optimization problem. In general, that problem is quite difficult to find optimized indices. We'll talk about that at the end of the third day, and how commercial kits aren't really optimized that way. But you can imagine that there's some complexity level that if you got 6 mers or something, you need minimum distance or something. There's going to be some number you can do, and that's it. So if you have a situation like Amplicom, something, whatever, where you don't really need much throughput in each library, but you want a lot of libraries, then that's a problem because you can't label them all. And so I think the original motivation for dual indices was it was simply a way to get 4 indices, right? So if I can prime it in another place effectively and sequence another 6 bases, and then in my library preps, I can sort of make one of those be one end of the adapter on one side of the read, read and the other one's on the other adapter, and sort of those 2 adapters can come from different tubes, and then make your library step kind of grid system going on, right? Where it's like all the rows are going to get the right-hand half different indices, and all the columns are going to get left-hand half different indices, and every intersection will have a unique parent. So that was the idea. So then with 6, so suppose you have 12 6 mers in your plot, that's what you got. And it's not like the I1s and I2s have to be the same sequences, but maybe you got 12 possibilities for I1 and 12 possibilities for I2. Well, if you only had an I1, you only do 12 plex. That's the maximum complexity. But if you have the pairs, you can do 12 times 12. You can do 144 for basically the same technology. So I think that was the original motivation. There's a stupid motivation now because there's index hopping, which we'll explain in a second. And indices can be much longer now. So in fact, most the Illumina kits these days on the Nova seat will allow you to do 36 extra cycles. So, you buy a 100-cycle kit from Illumina. Right? You got to buy the flow cell, but then you got to buy the SPS, so liquid reagents that have polymerase, prenucleotides, fluorophores, terminators, all that stuff. So they're sold in like 50 cycle bots, 100 cycle bots, 300 cycle bots. Sure. So suppose you buy the 100 cycle bots. Well, okay, you could do a 101 base single main read that'd be fine. Or 100, 101. Or you could do a 51 plus 51 base paradigm read. That also has that's 102, but basically that's the same. Now you may think, oh, it's 100 cycle kit. It's used up. No, because they got to allow for index cycles. It turns out they generally allow for 36 of those. So you could do with 100 cycle blocks nominal. You could do 51, 18, 18, 51. Well, 18 is a lot bigger than 6. And so these days, you can have sets of indices that are very large, but still maintain pretty decent distance from each other. And so that's not an argument for why you need dual. Even one, I want to is not firewall is saying, yeah, we'll see if the recording. I wonder when that popped up, how long that's been. That's the recording will have a jump. I don't know. Okay, so yeah, because of this index hopping thing, you don't want to do dense duals anymore because you'll see why. I mean, it's hard to explain it. You kind of go through what dual indexing is and work through an example. Basically, because of this indexing hopping phenomenon, high density duals don't want to do. So the way you do it now is, okay, you've got a long I1 and long I2. You make it so that I1 alone can uniquely identify the sample. I2 alone can uniquely identify the sample. But you still do these unique combinations of I1 and I2. You only use each. For each I1, you only use exactly one I2. So match up your I1, you have an I1 list that's 96 long. You have an I2 list that's 96 long. You match them up 1 to 1, and you never use pairs except for the ones that are next to them. That way, if something weird happens, which is index hopping, the effect may be that you see an I1 who is not coming out with the right I2 well. That's not supposed to happen. That means something weird happened. It means like anyway. So, but then because you've got so many combinations that don't match what your expected list is, it allows you to detect most of them, and they just get ignored because you can throw them away. They won't land in one of your Demux files that you actually have as a sample. Right. So that's called a unique dual, and that's really what people do dual indexing for now. Okay, so to explain kind of what all this is, we got to work through an example. Plus, you want to know how to do B-sub FASTQ2 on dual index lines anyway, and I sort of want to show you the empirical kind of approach for dual indexing as well. So it's a lot to do. This will probably take, we got an hour and a half left. I'm expecting it to take all that basically. So also duals tend to be big these days. Like 96 plex unique duals. That's a very common one. It's 96 well played. So that's a really painful to do. So we're going to do a tiny one, meaning only a 12 plex. And it's also an interesting one because it's not a high density dual and it's not a unique dual. It's in the middle. It's a 8, so it's ZBPO 9991, which I didn't get permission to share, so that's why it's not visible on top. It's a PE 5151 on the main read. The index reads are 8 with 8 dual. So I1 is 8, I2 is 8. The intention is a 12 plex for the sample. It's a non-unique dual. I1 is actually distinct and uniquely identifies the sample. It's 12 distinct I1. But there's only 6 unique I2. Each of those I2s have been used for exactly 2 samples. So again, we're going to start from the raw run folder, which is in the Hoffman directory. Now the cycle breakdown is 151 is SE, 5259 is I1, 6667 is I2, and 6821 is 50. So we're going to need the index reads to, of course, to proceed to do anything. So the first thing to do is throw in B-sub FASTQ2, generate some index. There's our command line, which we've seen before. It's basically the usual thing, empty sample sheet. But now our use basis mask is going to be, because the main ends have also been deleted here. Y150, comma I8, comma I8. So this is now I-end dual part. We're going to get I1 files, and we're going to get I2 files. And then comma Y1 and 50. Okay, and goes and gives you the non-demux run. So, you know, here it is, wherever, 99 now, 99 non-demux here. So there, let's CD into it. All right, so this is, you see here, we've got an R1, which is main end one, which is only one base, because it's, you know, that. But we've got an I1, that's our 8-base first index. And then we've got an I2, which is our 8-base second index. And you remember when we talked yesterday about the order that reads appear in files, it's always by physical order on the flow cell, increasing tile, increasing Y, increasing X. That means files that have the same subset of reads, since obviously corresponding lines would be perfectly the same. So the nth line of each of these files corresponds to the nth line. It's the same well as the nth line and all the others. That's guaranteed. Okay, so we will need an I1 histogram, we will need an I2 histogram, and we will need a histogram when they're taken together as sort of a 16 mirror read. Those are straightforward adaptations of the histogram pipeline that we did before. Here are the commands. Maybe the only interesting one is how do you do the paired guide, because it's in separate files. Well, obviously this gzip paste cut F2, that gives you, spits out just a one column list of the I1s. This gives you, spits out a one column list of the I2s. And then this is a bashism, which you don't, it's really worthwhile if you're doing bioinformatics. You should learn as much about bash as you can. I mean, there's many, many pieces of goodness inside bash. So this is like the redirection less than, but I've got a redirection like with a parentheses in it. So that makes the thing inside the parentheses a whole pipeline. And since this is a read from redirection, as if you were pulling in from a file, what that means is that this pipeline is run and the final piece of it produces standard output. That is now treated as a virtual input file to this command paste. It really turns into a file name, something like devfd63 or something like this, whatever, which is I don't want to get into Unix and what file handles are and all this stuff or whatever. Basically, you can kind of, it's not really done this way. You can kind of think of it as like this pipeline writes into a temporary file and that file name is given to paste and then it reads from that file. Except it doesn't really make a temporary file and it's done only in memory and whatever. But basically this is like making making kind of a virtual file that's the output. It's just got the I1s. This is a virtual file that's just got the I2s. And then with paste, we get those in two synced up tab separated columns, right? So this little ditty here, there's our paired up I1 and I2. Well, obviously that's easy to do. Now we just finished with the usual thing: sort, unique-c, fix the space to tab fit business. So of course now there's column 2 and 3 will be the two indices, and column 1 will be the count. So it's all whatever. But and then we want to resort that by descending order, which is now reverse numeric on the third column, and then just for, so it's a well-defined order, then break ties by the first column, then break ties by the second column. So that's how you get the histogram for the pair. So yeah, I've got them pre-computed here. And I mean, you can play with these commands on your own time now. Just to keep us moving quickly, I don't want to run them all live right now. But so there is the I1 histogram. And I mean, you can already kind of see how this doesn't take much, right? We can put this into impure Demux checker, right? You know what? Yeah, might as well do one of them. I probably won't do both, but helper or whatever I called it. Okay, I'll even leave this off. We got to compute how many PF1s are in this lane if we want the percents to be accurate in that thing. I must have done that somewhere here. Here's the number of PF1 wells in that lane, computed the same way we did before. You can just use any of the histograms to do that. They all total to the same thing. They have to. So there's the total number of wells now that are PF1. And here is the top of the I1 histogram. And obviously these look like they're good. And then here's a big drop off. And then, just to go in a little bit, well, let's go down here. Obviously this is already in sort of the tail. Where's the Firefox? Okay, so there we are. Okay, so looking at this. clear it. Well, we got to start with one mark. Well, I mean, we can always unmark things later. So let's just mark the things we think are obvious, right? So that's poly G, that's phi X. And then there's the big thing. So, okay, so how does this look? Make my window a little wider. There we go. They're all one to the line. Actually, what? You got to go further, right? You got to do this one. Oh, no, actually, here's an interesting case. I promised you that indels happen. Well, here's our first example. Because I'm like, oh, I'm looking down this column, I'm thinking, oh, I didn't have that guy marked, right? Because he's past the representation break, probably not real, right? Well, he's 3 mismatches away, right? I was looking down this column, I'm like, oh, a 3 mismatch guy, I didn't, he's right next to this guy, I should probably take him. But then look at the next column, which is the indels, right? He's only 1 indel away from number 4. And here's the representation break. He's an indel corruption of a guy. Right? So just to see that, okay, that's the one we're looking at right now, the number 15 or something, and he is oh, it's number 14, really. This is number 14 in rank ordered in the I1 empirical histogram, right? If you want to, it's like sort of like HI1 14 or something, right? Using our R-like terminology or something. And who's the 1 mismatch to? Number 4. Okay, so we got to go to 1, 2, 3. It's basically this. There's the alignment. That's a high systematic indel corruption. So those are but then basically if you bounce between these two columns, it's like 1 1 1 1 1 1 1, and you can, this is very, it looks like we're done, right? We've got the empirical list of what's present in I1. Done. Same thing with I2. I2 the same. The logic is basically the same. I'll do a third example, right? You can see you can do these pretty fast once you're kind of into it. Right, so there's the I2 top. And I told you in I2 we're only expecting 6 from the user, right? Each one should be used twice. So you'll see here that the representation counts are higher. There's really 2 guys each. So okay, 1, 2, 3, 4, 5, 6. I'm cheating because I'm not supposed to know that there's really 6, but clearly there's a big break there. But actually, it's kind of like a mini break here. And now past this point, kind of looks like anywhere to the tail. So anyway, we'll take a few extra. Go back here to Demux helper, and let's see what this looks. Okay, well, obviously we know that a bunch of these at the top look pretty good, so let's fill those in, at least to there. Well, at that point, everything's 1 mismatch to the previous list. So that is actually 1. Well, that's 8. How does that work? That's like, and you see these are 3, 5, and 4 mismatches away to the previous. So I shouldn't unstar these. They're also not indels, big indels. So these 2 look real here. But what is this? Well, I'll tell you, this is actually the way phi X I2 sequences on NovaSeq version 1.5 chemistry. So this is expected. This is basically the I2 for phi X. This poly G dark though for I2 isn't really expected, but it's kind of here. So this is like something dark in I2. We don't know. No, that's kind of unexpected. We'll keep it. 2 million of those with exact matches only. That probably pick up some more with the 1 mismatch or something, but we'll keep that for now. But so anyway, these 6 are probably the user. That's phi X, and this is an extra. Something dark. Remember poly G is dark. So it could be a lot of things because it's just something that didn't prime probably in I2. But there's our list for there's our 2 lists of empirical canons. Okay, and then we will put those in 2 files so that R can pick them up later. They're sitting in Hoffman right now. And now we come to the pairs. We understand the I1, I2 situation. Now let's look at the pair situation. Well, this is where it kind of starts getting interesting. Okay, so let's look at the top of the pair. Okay, that looks like this. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. That's looking pretty good because here's a break. That is phi x. That's, don't know, we'll keep a few of these, whatever. Now, this is where it's a little inconvenient to use empirical Demux helper because it doesn't understand, whatever. I mean, these are not mature tools. They're not really the tools I use internally as I study Mathematica and whatever. So unfortunately, you kind of got to get rid of the white space in between if you want to use this tool as it exists right now. So how would you do that easily? I can copy that, paste that into a text edit document, use my column selection with the option key, and there we go. That's actually a histogram that it will accept. Okay, there we go. Okay, and we might as well mark the really obvious cases that look good. Okay, actually, this next one looks like we probably should keep it too because it's high indel, not close. Well, then that's a one mismatch. Here, of course, the analysis is taking these 16 mers as a whole, which is, it's kind of the way B-cell the FASTQ2 thinks. In R, we're going to do it a different way. In R, we're going to keep the I1 analysis separately from the I2. We'll keep them as paired. But essentially, we'll do on I1 what our single end analysis was like. We'll do on I2 what our single analysis was like. Then we'll look at C. Now that we've kind of resolved the I1 and I2 separately, then we'll see what the pairings are like. But you can kind of work with this tool with the paired in data like this. And basically, well, actually, it looks like, this looks like kind of a pair. Then the next one, two mismatches. Two indels is a pretty big. It is 6 mismatches away, which are much more likely than indels anyway. So one indel, yeah, okay, maybe two indels is like a rare multiplier versus the 6 here. Yeah, I don't know. I mean, at this point, we are petering down and so on, and maybe we do need the full analysis to really make more intelligent decisions at this point. It certainly looks like kind of like, let me put it this way. There is no really super high representation pair that we haven't already covered. You have to check and you look at these guys and compare them to our I1 and I2 list. But if you compare these that I've marked to our I1 and I2 list, we've already covered all of the first halves and all the second halves. So the pairs does not discover any high representation thing that we're not already going to cover by having all combinations of our existing I1s and existing I2s. So basically, we're not going to really worry too much more about this analysis because now we're going to go to R, do a full I1 analysis in our style, do a full I2 analysis in our style, summarize those based on the I1, the tangent I1, the pile that the I1 goes into, combined with the pile the I2 goes into, and then look at that matrix and make some decisions about which pairs actually exist. So that we kind of already have applied like a one mismatch tolerance or something to the two ends before we make our decision of how much tallies exist in each grid square. So that's the plan. So, but sort of at this level, if you kind of go and compare this list versus our canon list here, which I'll just to get the names shorter, let's name these guys just A through M for the I1s, and let's name these guys 1 through 8 for the I2. And that way we can talk about pairs like A3, B6, whatever. It's a very fast way of saying a pair name here. So if you do that, and you kind of convert these to that naming system, everything above the line here, these are all exact matches. So the I1's an exact match to our canon, the I2's an exact match to our canon. And these are the cells that get filled in, A1, B3, P2, so on. Then as you go a little bit lower, it's like, oh, this is actually, well, this low one, I can't really explain why I got them gray here. Maybe at the moment, the decision between gray and not gray is just, are you in this kind of passive representation breakdown? That's an exact M4. Actually, I mean, there are 12 already. That's the 12. That's the user 12, almost certainly, right? We're not really expecting any more, but now we got M4. Well, that's the user 12 plus phi x. The M7 is the phi x. There's 13 of them. and the M is the phi x start first axis. So actually, so here's some weird pairings where phi x isn't having the right I2 or something. Well, what is that? Well, we'll talk about that in a second. But yeah, anyway, we're not too worried about the M's yet because that involves a phi x guy. So it's dark for its index, so, whatever. But then the next one is I5 with one mismatch in the I2. Then an M3, an M2, and an M1, more weird pairs with phi x start I1. Then there's E5 with one mismatch I2. Then there's M6, another one of the M's. Then there's B8, which is our first one that involves that poly G I2 that's dark. Well, again, we're not as worried about those because they're kind of, we know the user stuff is sort of this A through L and sort of a 1 through 6 part. Sort of this, if you drop these kind of last two columns in the bottom row, we know the user stuff is sitting in this upper left corner of the matrix. But then we get actually a D4 with one indel in the first guy. We know those indels have got to show up at some point because we saw them in the I1 and I2's list. So I mean, at some point they've got to show up fairly high. We had this one and we have this one here. So yeah, it starts to show up as a pair. There's a D4 with one indel in the I1, and so on. Okay, but this is getting tedious. We kind of want to do this in R now because this list is very long. I forget how many. How big are these histograms, right? In terms of just number of distinct sequences that are being recorded. Well, it's like 26,000 guys for the I1 and I2, but it's 400,000 guys for the so it'd be nice to switch to R as the analysis method. So do the whole histogram and not like just the top. So basically what we're going to do is exactly the same thing we've already done for the single end analysis. But we're going to do it independently, straight up single end analysis like we've already done on I1 independently, then on I2 independently. Then we will look at our pairs, process the pairs via the I1 analysis and the I2 analysis, and then tally up a matrix using those little single end analyses and make the paired matrix. And then we'll look at the matrix and make some decisions. So basically, the R code I'm showing you here is all stuff you've already seen from the single end analysis. But because we have to repeat it 2 times, it's nicer to make R functions so that we can just not have to just copy and paste code and edit the code all the time. We can just call the functions with different arguments and achieve the same analysis. So basically, the first business here is just to parameterize the stuff we did in the single-ended analysis so that it's easy just to plug in. Oh, here's the I1 histogram and the I1 canonical list. Go do your business. Here's the I2 canonical histogram and the I2 canonical list. Go do your business, and then we can run the code twice without copying and pasting it, like making hand edits. So that's all we're doing here is just setting up some functions to make the kind of the repetition easy. And we got to, of course, load the data. So the data is sitting in the same Hoffman directory it was before with some different file names now. So we need to read the H1, the I1 histogram, the I2 histogram, and the paired histogram. Okay, of course, the paired histogram has extra columns, which is why we have to have some if-else's inside this read table to handle the fact that the paired one has an extra column. Okay, so let's read in the data. That's live pulling from Hoffman there. You can see how convenient you can kind of get it going, right? Like get index histo Hoff for a Hoffman path, and then just feed in. I put the directory and name in a variable, so I don't have to type that all the time. And then I just basically put the file name. Default's true is whether it's a single or paired end to control whether the number of columns is one or the other. And then to keep all the names straight, let's put different prefixes on the names there, just so that we don't, less chance of confusion there. But anyway, yeah, so there's the top of the I1 histogram, there's the top of the I2 histogram, and there's the top of the paired histogram. That's all nice. We have the histograms right in. Now we need to get the list of canons that we decided there, the I1 canons and the I2 canons. So let's read those in, and there's the list of it. Okay, now we actually have to do the Demux analysis. Remember, we have to do the business of comparing each guy to all the canons and then finding the minimum distance. And if it's not unique, it's Demux fail. And if it is unique, that's your guy, that's your pile, and so on. So here's that Demux process as a function. Boom. Now we need to do the I1 analysis. right there. If you're a programmer or analysis or something, but the machine is busy, but you're going to be playing Nerf ball or something, right? You do something else, compiling, waiting. It can't possibly be doing anything else. Okay, and we need the I2 analysis. You see how easy it is for progress bars. It's super handy. Otherwise, the thing would be sitting there. You have no idea. Am I 1% done? Am I 10% done? It's so easy. Progress bar. There we go. And now each of those now has the extra column that we added there. Now we need to do the transformation to that summary matrix, right? Where we organize that matrix by canon target on the rows and mismatch distance on the column. So that's the dplyr tidyr stuff, but we can functionize it. There we go. And now we need to summarize I1 and summarize I2. That you can see that's almost instantaneous. And there they are. Okay. So that's basically the complete I1 analysis and complete I2 analysis with arbitrary Demux. Okay, now let's make the plots that we made before to decide what our Demux tolerance would be. I mean, it's going to be one, but let's keep ourselves honest here. That's the number of PF1 wells in the lane. These are the percentages. Make sure the names on those are correct. We put the percent of less than or equal to one mismatch that leaves the one mismatch tolerance, say, and then let's just make a bunch of plots. Put them all in one plot. There we go. All right. So what do we got here? We got the lane overall recovery on the top, and we got the per target view on the bottom. And what's the story? Well, you always got to look at the y-axis too. Right? So the per lane recovery benefit from one mismatch. This only goes to 3%. But there is still number 13. Up there, of course, number 13, I think is what we don't think is really either anyway. So I'm not sure about that one. So we're down to more than 1%. That's only. The scale here is a little bigger. That says here 10% about. Again, it's number 8, which is what? That's bias polygon dark. No, that's the polygon dark extra. I'm so worried about that. But yeah, it's not like the user ones are probably the first 6. This is bias. Actually, I mean, even exactly. But look at the recovery, the overall recovery. It's sort of a broad, modest benefit for one. I'm not really worried about, given that we've seen the cost of experiment. It doesn't look like super high error. It's not like an unusual way. Maybe we'll accept the modest. Unless things push us out of it. It's not really not too much. Anyway, we'll do one mismatch for I1, one mismatch for I2. We've at least checked, right? So now it comes time to do the analysis of pairs. Right? So now we're back to doing new stuff, right? We're not just repeating things we've done before. So how does this work? Well, again, defiler to the rescue. So you can do this thing called a left join. We essentially have 2 tables. We have 3 tables, We kind of got to mush them together now, right? So we've got the I1, and then we essentially want to take for each row in the pair histogram. We need to find the right row in the I1 analysis and add its data to make the row bigger. And for the I2 in each row, we need to find the I2's analysis row for that, add his data to this. So we need to merge our tables together. So the database scheme right here is called join. And then the various kinds of joins, left, right, outer, inner, anti, whatever, they're all related to how you handle rows and don't match. In this case, it's really not a problem because we know that the I1 histogram has every single MER that's in the pair histogram and sync with that. The subset of distinct indices that are present in both of these, all these lists, all of them. So the different joins don't really matter. Logically, I suppose it's the left join. Left join is where the table on the left, which is, we'll start with the pair table on the left, and we're adding stuff to it. The output has the same number of rows as that table. So if the other guy has missing rows, they still, that row still comes over with the missing data for the living there. And if that guy has extra rows, they don't create extra rows. So like I say, it's all going to be the same subset, but it doesn't really matter. Logically, it's kind of left in the sense that we start with a pair table. We want the output table to still have exactly the same rows as the pair table with extra data. Not just a left join. The left guy controls the business. So we need to do two left joins because you join in one table at a time. So start with H1 I2. Then left join in info from the I1 analysis. The columns that you use to match up or look up is on the left table, it's MER I1 column. On the right table, it's the MER column. You could have named the MER column in the H1 I1. In general, there's two column names. So that's the way we want to look at it. Whatever's in the MER I1 column on the pair table, we'll find the row in the I1 analysis that has that in the MER column. That now identifies the two rows that are paired up. Okay? The suffix is a little hard to explain. It's just that when you put the table together, you may end up now with columns that have the same name. So we have a tally column in pair histogram. We also have a tally column in the I1 histogram. Maybe we should have called it tally I1 and I1. But whatever. At the moment, they're both called tally. And you can't have two columns in a data table that have the same name. So somebody's got to get the name. So the suffix thing says that when there are conflicts, the same column exists in the two tables. And it's going to keep both of those columns. Somebody's name has got to change. The suffix is the string to put on the end of the column names to make it. So actually, that I want on the left side table, don't change its name at all. On the right side table, you can tack an I1. So his tally will become tally I1. And so that's it. So then the left join will do. And then I actually want to rename the columns a little bit because we're getting more confusing about how many next left join. So what have we done? We've added 3 new columns because we brought in the disk MMmin, the mismatch distance for that I1 analysis. And we brought in the disk MMmin act, which is the tile that the I1 analysis set goes into. And we also brought in the I1 tally. And those 3 columns. We just renamed I1 tally as tally I1. I decided it's more important to put the I1 in the front. The left join only lets you do the suffix on. So I let it put this suffix on, but then I'm just going to rename it so we put it on. So we renamed tally I1 tally. And the other 2 columns that we added don't even have an I1 item yet. We're going to get 2 more of those from the I2. So just to save ourselves from having more naming conflicts, next step, let's rename this MMmin I1 this MMmin I1. Now we're ready to do the next join and bring in the I2 analysis with less naming, which is here at the point. So again, we now bring in the I2 analysis. That's a MER I2 column on the left with the MER column on the right. And then the conflicts, which will be tally again. It's an I2 summit. And then we do the same renaming we did for tally I2 is now tally this add or not I2 and just to be absolutely clear, we'll actually rename the tally column from the pair file tally I1. Now and then depiler absolutely hates row names because that's the whole tidy philosophy of the tidyverse. They don't like special column magical columns like row names, but we'll put them back. The rows never changed identity order or anything during this whole operation. So because it's a left join, so we can put the row names back and back to the way we were. Okay, so and then what does this look like? So now the I1, I2 tape, the pair histogram file has now grown a whole bunch of new columns related to merging in the I1 and I2 analysis. Right. So now this is the same pair histogram. There's the raw file that that's the file that's sitting on top. But now we have the I1 analysis on the I1, and we have the I2 analysis on that already, all paired up. Okay. So now we want to make the summary matrix that we were talking about. We already decided that we're going to do less than or equal to 1 Demux tolerance on the individual I1s and I2 analyses, right? So that means that we're only going to pay attention to rows now in this histogram where this number is 0 or 1, rows where this number is 0 or 1. And then we're interested in the pairs of these are the piles, right? So then this says, okay, so like this first one is a 0 mismatch, 0 mismatch. Well, that obviously meets our less than or equal to 1, less than or equal to 1 requirement. And this says that you should take, it's pile 1, comma pile 1. It's the 1, 1 square. And he gets 68 million entries added to it. Right? So basically what we now need to do is cut down the rows of this file to ones that meet our mismatch requirements, throw away the guys that are Demux fail, and then form a matrix of the result where the rows are indexed by our I1 targets, our columns are indexed by our I2 targets, and the entries are the sum of all the tally I1, I2s that meet those requirements, right, that belong. Well, okay, how do we do that? Depiler, of course. So start with our new augmented dual index histogram. Filter means pass to a subset of rows that meet the following conditions. The I1 mismatch distance has to be less than or equal to 1. The I2 mismatch distance has to be less than or equal to 1. The pile, Demux pile for I1 can't be Demux fail. Here I'm saying that by just saying it's less than or equal to the number of I1 targets because we use the 1 past the n for Demux fail. Same thing for I2. So these two filter lines now restrict us to the less than or equal to 1, less than or equal to 1 non-Demux fail guys. Okay, now we don't need all the columns that are left at this point. Most, we got extra columns now. So let's just keep the columns that are relevant. That's what select does. We're going to keep the column I1 dist mm at, that's the I1 pile, all right? And we're going to keep the I2 dist mm min at, that's the I2 pile. Let's rename those CI1 and CI2. It's the canon I1 pile and the canon I2 pile by index, 1, 2, 3, 4, 5, whatever. And the other column we need is the I1, I2 tally for that. Those are the 3 columns we need. These are going to become our rows. These are going to become our columns. And then this is the things we're going to add to put in the intersection of the rows. So for the same reasons we talked about the other time we summarized things, we want to guarantee that the matrix we give out has no skipping of numbering and something. So we're going to add a bunch of 0 tallies for every distinct I1 target and every distinct I2 target, just to guarantee that those all show up. And then we're going to group by row, column, summarize by the sum of the tally. And now we're going to call that tally less than or equal to 1, less than or equal to 1 mismatch. That's it. So that, that gets rid of, there may be many entries in our original table because, our original table is organized by the full 16 mer read from the pair of index reads. Guys that go to the same Demux files and meet the requirements in this method. We no longer care about the particular sequence that lands there. We just want the sum, right? So that's what this group by summarize ungroup is doing. is it gets us to the point where we now have one row for each unique combination of R1 and I2. Right? It's basically the matrix, but written as kind of row number, column number, tally. But it is only got one row now for each cell in the matrix. So next step is to make sure that it's sorted by row number first and then column number is tie break. And then again, it's a pivot wider, right? The pivot wider means we want the new rows to be controlled by CI1. The new columns are based on the distinct values of CI2. And the values that you're going to put in the square are from tally less than equal to 1 mismatch less than equal to 1 mismatch. If there's missing entries, they're 0. Okay, and then we'll end up with CI1 as a redundant column. Get rid of it. Okay, and that comes out as a data frame, I think, and then let's just make it a regular matrix and put the row and column names on it. And so that gives us this beautiful matrix. So these are all our canonical I1 targets, all of our canonical I2 targets, and under a less than equal to 1 mismatch, less than equal to 1 mismatch, Demux analysis. How many reads do we get? How many? One thing you notice is it's not like that's just got 20 squares with numbers on it, right? I mean, or 12. User has 12, right? We know the 5 is like, you know, these last two are rather 5 in the last column. But, you know, okay, user stuff is like this, you know, like 40 million, you know, whatever it is, 26 million. But we got off combo pairs of like 200,000. What's going on? It's not like there's a lot of zeros in that matrix. So let's make some heat maps. Heat map is a built-in R function. The library P heat map is for pretty heat maps, and they're nicer, so we'll use those. Also, for this kind of analysis where, you know, we've got orders of magnitude different things going on, right? Log scale, much more appropriate to visualize this data. So we'll do a log 10. I think our matrix has non-zeros everywhere. We could just do straight up log 10. Log 10 scale is always, you know, a problem because like you got zeros, right? Which are, you know, theoretically possible. So, you know, we could color those special color or something. We'll just do something very easy. I mean, the numbers are mostly in millions, tens of thousands of thirds. We'll just do log 10 1 plus, right? You know, the easy way, we'll just shift it right a little bit relative to scale. That's not too much anything, but it would solve the zero problem. You don't have to. Yeah, anyway, I don't really want to spend time, you know, I'd say, oh, we're not treating zeros completely right, but you know, whatever, it doesn't really matter for this case. So here is a, actually P heat maps default is to cluster the rows and columns, but you know, we kind of got them in rank order right now. Our targets are in, you know, our I1 targets are in rank order, the I2 targets in rank order. Let's just keep everything, let's not permute things just to confuse us at the moment. So we'll just tell it the first plot to make, don't cluster it, just give us this matrix in the straight up order, we got it. Okay, don't get too fancy on us. But there, this is quite an informed, you know, this is a very important matrix here. I was hoping the font size would grow. There are arguments for that, but oh, yeah, I can do it this way. Copy that, put it in preview as a PDF viewer at that size. Yeah, and then it'll scale it. We'll lock in this kind of a thing at that point and then zoom that up. So it gives you a chance of reading the numbers. Okay. So the numbers you see are literally the entries of the matrix. The row and column names are around the edges there. The color bar for log 10 representation is on the right there. So that's, you know, the bottom is basically 1, 10 reads, and the top is like almost 8, which is 100 million, right? And then the color in the square is just a conversion of the number to color just to visualize it. Well, clearly you know, clearly the pairs are the pairs, right? I mean, these red squares are very salient, right? I mean, this is the, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's the 12 user log. This one down here in orange, which is the next hottest one anywhere, is 5x. canonical flags, I1, I2. Then well, this is all like yellow, right? You know, it's not like this is blue. This is index hopping. Okay. So there's different mechanisms for this, but I don't think we really have time to get into the mechanisms. So you can read literature and online discussions on how this can happen in various ways and so on. But basically, there's two kinds of points in time where it can happen. During library prep, where samples are being handled in batches and so on. And of course, during library prep, all the reagents to attach adapters to samples are sort of active and so on. You can just imagine things can happen there where sort of like the groups of samples meet each other, chemistry might happen, or whatever. I mean, maybe some guys get the wrong adapters on, right? Because maybe they weren't perfectly clean before you mix them together. So yeah, so it can happen in sample prep time. And it can also happen on the instrument during exam. For example, if you have a lot of free adapters left over, like you can clean up the library very well, and then you've got some free adapters around, they can be polymerizing too and well. I mean, as I say, I don't really want to get into the details of the mechanisms that happen. So basically, there's ways it can happen during sample prep, there's ways it can happen on the instrument. And the end effect is samples have the wrong barcodes. Now, we're only seeing this because we ran a dual design with a lot of empty squares. But this is happening all the time, right? If I had run this library as single index, you think magically the hopping would go away? No, we just can't observe it, right? If I ran this lane as single index, what does that mean? It means I only know the I1 identity of the sample. That's like knowing only the row number. I do not know the column number, which means that in a Demux analysis of I1 alone, what goes out in a Demux pile is the entire row, right? The entire row for, no, I'll point to this one. But you know, this is number 12, right? So this is a 12th I1. If you did it as a single-ended run, the Demux pile output for I12, or for number 12, would be this guy plus 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 this guy. And all these guys, which are basically things with the wrong pairing of tags on, they would all go here, but you wouldn't know. And so they would essentially create contamination in the plot. And so it's really the dual that lets you see that this is obviously happening. Now, like I say, if you had other ways of checking the Demux, if you have amplifiers, you could do this even a single index, you have some way to cross-check if you really know directly. But these duals with empty holes in them make it really hard to ignore that this thing happens, right? So they just make it really obvious that this happens. And in fact, I think in this line, well, we'll do it in R in a second, but in this line, I think it's about 1%. It doesn't, I mean, maybe these numbers look small to you, but remember that it's really like the whole sum of the row that should matter, right? So it's these individual squares are like 100,000, 200,000. And some of these libraries are like 20 million or something like that. And then I've got to do like 50, 1, 2, 3, 4, 5 of them. So like 5 times 200,000, it's almost a million there, right? So now it's like a million versus 20 million. But that's like a bad case. I've rounded up the numbers in bad direction. So it's like that make I think 5%. But the overall average is something. Well, that's not great, right? That's a 1% contamination of what kind of looks like you're everybody to everybody. Right? But that's reality. So what would happen? So okay, it's now clear. If you run this as a single index guy, it's still happening. You're just not going to know. The files will be. If you had run this as a dense tool, right? So if you had made use of all combinations of I1 and I2 and filled this thing up with libraries, you can't observe it because every square is a thing that you're calling a sample. This hopping is still going everywhere, but you just don't know. You won't be able to see it. Here, everything that lands in a wrong pile is not so harmful to us I mean, yeah, it looks like it reduces coverage, but it's better to reduce the coverage because it pulls them out from the file you were going to put them in, right? The alternative to not losing a little bit of coverage from these was to put them in this file and have them miss schema. They were dead for coverage whether you knew it or not, right? The far worse problem is that miss schema, right? So without the ability to have them land in empty squares, you would be miss schema. So that is why you want your duals. You want, first of all, you want these. Second of all, you want low density. What's possibly the lowest density dual you can make? That is where I1 alone is enough to decide, I2 alone is enough to decide. If you put them in corresponding orders across rows and columns, it's essentially the red squares will just be a diagonal with all other squares. That maximizes the ability to both detect and reject index hopping. Now, even a unique dual does not make index hopping go away, right? Because it's still possible for like somebody like here to hop to here, say, but it's hard, right? Because what's index hopping? It involves some kind of event where the I1 is wrong or the I2 wrong or they both got wrong. But maybe the ones where only one changes are easier to do and the ones that take two changes are harder to do. But here, with a unique dual, if you change just I1 or just I2, you'll never land on another declared pair because you've made the unique pairing thing. And so that's really good. Unique duals, single, either I1 or I2 is the wrong label, they always go into reject, won't go into a sample schema. Here it's not quite a unique dual because while the rows are unique, the columns got two guys. But that's still way better than a guy that say focus like got 50% or 80%. So here, if I1 change, if I2 changes, that's moving along in the row, right? If I make the I2 wrong, then this guy moves to one of these other squares, which are all rejected. If I1 changes, then he's moving around in columns. Most of the time, it's a question of whether it's random or not. In this case, this one looks fairly even, right? It's not like a lot of substructure. So let's just say, for sake of argument, it looks kind of random, like this one I got into. Well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 other places he could go. 11 other places he could go. One of which is to a guy that's another pair. But maybe you've got a 1 in 11 chance now that you get unlucky. You got a 10 out of 11 chance that it's properly rejected. So this is still more valuable than density, but not quite as good as you get really unlucky, both I1 and I2 change, in which case you're jumping from here to somewhere else on the whole chart. Then there's, in this case, 12 squares out of, what's 12 times like, 6, whatever, right? It's like 12 out of 12 squared minus 1 for the one you're already at it, divided by 12 times 6. That's like the number of squares that are empty divided by the number of squares you are minus, not counting yourself where you're starting from, assuming errors. So, and then you should also subtract with the lower column. But anyway, you see how it works. So the ideal is the unique dual, and it helps you find these things and remediate them by giving kind of a place for them to go. Not in a samples pile. It's very helpful often to do the clustered versions where you're allowed to permute the rows and columns. In this case, it's not too exciting, but for complicated cases, it's very helpful to find cases where the batch effects from library prep are the responsibility. Because then this will group samples into groups. It's clustering. So you can find clusters, and you may find that the clusters correspond to things that happen in the web. Oh, I process these 8 tubes together, then these 8 tubes together, then these 8 tubes together. And you do this and you see, oh, nice little hot spot of hopping here and a hot spot of hopping here. Here, of course, the clustering is going to group the two guys that are both sharing, the IQ. Okay, you can see that the phi-x hops here are very much in one direction. This is blue, which is low. Phi-x hops, which, I say phi, but it's not necessarily phi because it's probably dark. But mostly you see poly GI1, user I2, it's much more rare to see user I1 bias canonical IC. We've also got this poly G IC. But those are second order concerns relative to the index hopping that's filled up with this grid. Okay, so that took a little longer than I expected. It's 11:20 now, so time for another break, I guess. But, also, any questions? We haven't talked about UMIs yet, but it's sort of the ideal library preps are dual index UMI. It's easy to say, but protocols are protocols. You can't just wave a magic wand and make everybody do unique dual UMI. Library protocols are entrenched. It's sometimes not trivial to actually modify protocols to handle, do those things. People have long-term projects. They want all the preps within the span of the project to be consistent. Dual UMI, unique dual UMI, more expensive gradients. Sample, cost of sample. Tons of reasons. Trying a new protocol, always a risk protocol. But, validated a new protocol on the kind of samples you run. Lots of reasons why a lot of inertia in library. People run a lot of single-ended library. People still run single-ended 6-mer. It works for them. And they have experience with it. You don't want to change it. You have to really, to get people to replace, you really have to give them good reasons. But, hopefully, I'm trying to show you some good reasons. Kind of really try to get things easier to say. Okay. Oh yeah, so if you look at the user sample sheet, it turns out this is the pattern that you should get. And it matches, right? We got these extra guys in some, but the upper left corner where that's the exact pattern. That's now the point where we check for concordance against the user sample sheet. All right, let's try to get some numbers on index hopping, because I said it was like 1% or something. Well, let's actually compute it and verify. For that, we will need to know, R will need to know which are the squares that are expected, right? So, the user design is, what I just showed you, but those are the squares we need to count as correct. And, they're not necessarily, those piles are 100% correct, because, there can be hops into them, and we think they're rare with this kind of thing. So it's not like these are pure or whatever. It's just, they're probably getting hops at a similar rate to what the other squares are. But of course, these squares out here are zeros, getting things like 50,000, 100,000, 200,000. These squares are like 50 millions, probably getting about the same or something. Whatever. So it's a percent doesn't look bad, or at least it's not, it's not crazy. Right? We want to compute the number, which is what. Anyway, we obviously can't really know for certain how much is in here. We can kind of estimate it, and our R code isn't going to really estimate it. But, if you had to estimate it, you would extrapolate something like, well, given the other nearby cells or something, how much do I expect with this file? And then you would assume that the total here, you would subtract out that expected amount, that over that, whatever. You could work out kind of some estimate if you had to. But normally for this kind of analysis, order of magnitude is sort of sufficient to kind of decide how much of a problem it is. And so that doesn't require necessarily a fine figuring out of exactly those squares are kind of rare within the rows and columns, so they don't really affect the calculations that much for percents. So this first thing to do is just to tell R what are the user pairs, what are the expected pairs. So that is now in a little 2-3 column, like data frame. We'll number the samples. That's 1 to 12. What they really are. 5 from the bottom there. This is the I1 and I2 index in our list targets. And then you could give some metadata. This here all from project 1. This is 5. Depends on how much you want to automate your scripts and stuff. Auto adapt to sort of like a little metadata file. Okay, so we need to, okay, so this first bit of code puts together, oh no, not into the shell, please. Copy and paste is always dangerous with shells around. You end up with the wrong thing in your clipboard and paste it into the wrong window. Sometimes it gets exciting. Okay, so that is a little thing that just makes an all zeros matrix, then loops through the expected pairs. I think my paste is crazy. Oh, I guess that that connection lost internet or something, so it's disconnected anyway. We didn't end up pasting crazy stuff into a shell. Okay. So we start with an all zero matrix, and then we loop through these pairs here and just set them to 1. This is a very convenient way to, this is a compact way of encoding the information, but this, in terms of the counts matrix, is a much more easy way to use that information. We got zeros where it's unexpected and ones where it's expected. In particular, if we multiply that entry-wise with the counts, essentially it means that we'll only get, the counts that are where the ones are, and then we can add that up and get essentially the sum of all the places that where the expected is 1. And then we can always do subtraction if we want places where there are zeros. It's exactly what we're going to do. So here I just heat mapped it again without row or column renumbering, just so that you can verify that's the same pattern I was showing you. So this is now a 0-1 matrix with the ones exactly where the user expected pairs are, an incidence matrix, if you want to call it that. So now we can just do the quick calculation for sort of an estimate of overall index hopping. So this number, we take the tally matrix that the heat map tells you how many users, how big the Demux files are. Like this. We multiply it entry-wise with this. That kills everything that's not expected to be 0. But leaves the things that are expected to be multiplied by 1. So we basically cross up all the things you don't like, not expected to put 0 there, and then we add a column number. This is basically now the total amount of stuff that ends up in a Demux file that is a sample. And then, and let's just not worry about the phi-x and extra stuff right now. So let's just concentrate on the user-related I1 and user-related I2. So this is our Demux matrix again. The first 12 are user I1, and the first 6 are user I2. So we're picking out the upper left corner of the matrix that's going to be user part of the matrix. And we'll add a those. So this is everything that links Demux files with user pair. I1 is a user, I2 is a user mark. But that pair may either be expected or not. Whereas this number is just expected. So if we subtract those two, that's the unexpected. And then we can convert it to a %. So that is now, I wasn't showing what these numbers are, but there we go. So the subtraction then would be the unexpected. And then we can do percents. Right, so then we will 100 times unexpected overall. So that is the percent of user that lands in the ones, squares that we know. About 1%. That's our estimate of the missed Demux rate. It's a little slippery, like I said, because we haven't correctly accounted for the expected squares actually have some pop in them. And we can even estimate what that is, extrapolate it the other data. But we haven't accounted for that. This is sort of a 1.1%, obviously hot. Too hot and probably a little, whatever. And it's not going to matter much. The rest are sort of a low price, full grid. You get the idea. Order of magnitude 1%. That's what we got here. Which, in terms of the history of lanes, this is the higher side. Usually, it's fairly bifurcated. There are lanes that are kind of around this level, and the rest of the lanes, which is most lanes, is probably 10 times lower. It's like 1 in 1,000. Probably that's closer to normal. But it's not totally random. For example, same lab, same type of libraries, same people prepping, similar offerings. It is related to the material. It's not like a completely random. Okay. All right, we talked about the mechanism things. There's two kinds, the library prep time, flow cell time. There's actually a third way you can get things that observe as like look like index hops and actually affect you like index hops in the sense that like without the empty squares, they would be making misty mouse and samples pile. But their mechanism isn't either of those two things. People think of sort of the classical index hop. And that is if base call errors get so high that an appreciable fraction of the wells that really belong to that guy get so far away that they start landing in other guys' piles, right? So if I have some, maybe I have some two targets, which relative to the entire set of targets I'm laying, target distances. Say the target distances are all less than or equal to 3, or at least 3 mismatches. But it turns out that for this particular pair of targets, they're only 1 indel away. So the generic target distance here is greater than 3, which is not great, not terrible, enough for one mismatch, two. But maybe it happens that this particular pair has 1 indel mismatch, and all the other pairs are 2 indels away. So in a certain sense, in the all targets pairings, these two are kind of closer than anybody else. Now, suppose you've got one of these cases where the indel errors actually have a high systematic pattern that gets these two, bridges that gap. Okay. Well, now you got some of this guy bleeding into here or this guy bleeding into there, and the representation ratios are different. That's even worse, right? But maybe this guy is 10 times the size of this guy. Now it's even more possible. Well, what's that going to look like in this view? It's going to make a hot square. Right? It's going to start. If that one indel away is in I1 or in I2, but not both. Just like only the one side has the closeness, and the other side is still just fine. Then effectively what's happening is the I1 is going to become wrong, but the I2 is going to be right, and that's going to look just in this picture like an index hop. But it's very, very specific to sort of the sequence closeness of these two guys and the base call error pattern in the lane. So it makes kind of speckly patterns that are related to the guys that are sort of sequence-wise close will have hop, but other guys won't. And so that's not really thought of as sort of the classical mechanism. But effectively, it looks the same in this plot. And if you didn't have the dual nature, would turn into misty much, just like the other mechanisms do. You might as well call it index hopping too. It's just another mechanism if you like, but it's quite different mechanism than the other. It's not really related to chemistry and the library prep so much. It's more of an on-instrument base call thing, but it basically has the same appearance and same detection and the same effect. So might as well call it the same thing, index hop. And we talked about how this basically happens all the time. It's just that the low density duals make it really obvious, but it's happening all the time. And we talked about how you want to unfold a design as possible, which basically means unique duals. Also, another consequence of this and another reason why representation ratios are problematic is if you have index hopping and you have libraries that high representation ratio difference, 100 to 1, 1,000 to 1, you can have a guy that is very low true percentage because of the index hopping, right? He's a low rep guy. Everybody's hopping though. Everybody else is bigger than you. Their hops are bleeding into you way faster than your hops are bleeding out. And so the percent of you that ends up being hot, high. That's another way you can have piles, Demux piles, with low true fraction. And again, the major defense against that is don't pick high representation. Okay. Yeah, so we talked about this. This is the ideal, unique dual. When you get the I1 and I2 order consistent, then it looks just like that. And in this case, if you corrupt I1 or corrupt I2, you don't corrupt the other side, you're moving in a row or you're moving in a column, you always land someplace clean, someplace not going to be a sample. makes two errors. Both ends got to go bad to get this guy to go. And the fraction of that ends up being n over 2 over n minus 1. So yeah, bigger duals, bigger unique duals are sort of better. I mean, it's mostly more like a 4 by 4 versus like a 20 by 20 or something. That's got some difference. But 20 by 20 by 30 by 30 doesn't have some difference. N over 2 over n minus 1, it floats up to 1 pretty fast. But, yeah, if you have a very small unique dual, 4 by 4 or 5 by 5 is not as helpful as 20 by 20. But probably if you're doing unique duals, you probably have a bunch of samples on you. You aren't really doing low complexity unique duals. Okay. And we talked about this picture too, where if you were to redo this lane, it's a single index lane, which you can do here because I1 does uniquely identify. In some other light or something, or the user could have submitted this as a single index lane, whatever. But you'd be collapsing all these rows together. Right? The entire row would come out of one pile, and so all those hops would collapse. That value wouldn't be a group, unless you had other ways of doing it, like the Ampliton library or something. Okay. So here's a gallery of stuff we've seen. I could point to more examples than this. This is just kind of gives you some of the qualitative flavor and a little bit of the quantitative flavor when we see mixed-hopping what. And so you see there are cases like this. When you cluster the tons of stuff. This is a unique deal. This diagonal, I've carefully clustered here so that the rows and columns are consistent in terms of unique dual. This is still permuted, but it's permuted kind of row and column simultaneously so that you don't use the one-to-one nature of the design. So the diagonal stays on the diagonal. Otherwise, the diagonal disperses into little dots everywhere. For unique duals, you really kind of want to, if you're going to cluster this thing, you should really cluster the rows and columns sort of the same way. And what you see is, okay, the diagonal, that's the expected pair. And the blue is low. Blue is like 1, 2, 3 counts, whatever. All these are the same kind of long scale. Where it goes blue, purple. I think black is a real 0. Here I took the expense to actually make black. The 0 would be black. 1 then starts, I think, it's purple, and then it goes to blue, and then green, yellow, orange, and red. And that progression is a lot. So this diagonal, that's the expected group. But when you cluster, you get these big blocks, and you get these little diagonals like this too. In this case. This is a 96-well plate format. These blocks correspond to batches of samples. And these other lines correspond to, I forget whether it's rows or columns, but it's a physical arrangement of stuff on the plate. So clearly this is a case where something happened with sample prep. Because by the time you get to the instrument, there's no identity left from these things, right? On the instrument, everything's free floating and liquid. It's all mixed together. The instrument, what can the instrument hopping stuff look like? Well, that looks like this, right? This is obviously high hopping. I don't auto scale the color scale to start at the lowest number in the square. The color scale is forced to start with purple equals 1. Right. So this the fact that this is kind of yellow and green puts it, this is like the 1% level. I mean, if you look at the color bar for the guy who did make, where's the one where you still have the numbers here? Red to yellowish is like 2 points on a log 10 scale. That's 100 to 1. Right? It's kind of like the yellowish is kind of like 100 times down below the tops. The tops, of course, are the expected. So that's kind of the 1% level again. What do you see? It's just uniform. No structure at all. This is what like on instrument hopping kind of is. Sometimes you'll see, these libraries actually have fairly equal representation, but sometimes you have libraries that differ a little in representation. You see this guy here has more of like a yellow green in the upper left corner and blue in the lower right corner, and it's here the rows and columns are sort of organized by the descending frequency of the diagonal. You can't really see it on a log scale. But the one in the upper left is a little redder than the one in the bottom right is a little oranger. So you just see sort of they're organized by sort of descending frequency. And you see it's just kind of uniform, but does decay with that frequency. So the amount of hop contribution, you can see that this also tells you that sort of like row and column changes are the most common thing to happen. Because if you're a guy on the diagonal and you're a low rep guy on the low side, it's not great. If you're on the low rep side, you hop into rows and columns a little less because it's coming from you and you're lower. Whereas the guy, the high rep guy, hops into his row and column higher because he's a high rep guy. So here it's kind of clearly going kind of rows and columns based on fraction representation of the primary. That's what we find. Yeah, so these all show various forms of sample prep. This is a 2-project, maybe that's a 2-project, maybe it's a 3-project diagram. But the 2 big blocks there are the 2 projects that are mixed. Each project is hopping within itself. And I forget what the expression was for the kind of the cross hops. Maybe I don't remember that one. Oh, maybe it's just maybe that was 3 projects mixed together. I mean, there's if you notice, there's kind of a block here, and this is actually a little block that's even higher. But somehow, whereas these 2, once mixed, don't cross between them too much, this guy's more promiscuous. And here, what this probably means is that this is a case that's a mixture between on instrument and I don't want to say too much because I don't totally remember which one all these are and so on. It's not really, the point here is to not really get into the details. Just to let you know what happens, how it happens, what you should do as a design, which is unique tools, how you what to do, tools and so on, how you process like this and visualize the problem, and then you can make your own conclusions. How bad is it? Is there anything sample perfect better? But for example, what structure like this means though is that the cross contamination between samples is not all samples to all samples in some uniform percent. These samples are cross contaminating each other at a high rate, but not so much across this way. Right? So the cross contamination is bad. I mean, if this has some effect, I mean, this is 1%, whatever. There's all kinds of things. But if you have some analysis that actually is really sensitive to cross contamination, and you made some kind of PCA plot or something or whatever your samples are so on, and you get clusters, you're probably going to get clusters controlled by these blocks. So this is cross contaminant structure. Whereas things like this are kind of less problematic that way, but you don't really like it down to 1% everybody. That's not good. I mean, what you want to see is red and black, but you're not going to see red and black. What you want to see is red and purple, red and blue, not red and yellow, not red and orange, whatever. And the last kind is the speckles, right? So I don't know if I can see it from standing up here, but you guys are further back. But if you look at this one, it's kind of like there's a uniform background, and then there's like once in a while you get like these, in fact, even like orange. They're not even like yellow, they're like orange. They're just kind of little guys, little speckles here and there. And that is this base call driven version that we've been talking about. Where sort of certain pairs of sequences are sequence-wise close and will cause an I1 or an I2 corruption that's in such a way that you land in another guy's file, but the other half I2 or whatever hasn't gone there. So now you kind of see it in this view, and it's in the wrong pair file, and looks like an index. And effectively isn't an index, but it's a different method. And here's the case I threw in just because it's kind of an example of an almost totally dense unique dual, but it's missing one square. So it's not the full design. This is multiple projects again, where one of the projects is actually single indexed. And effectively, these single index libraries have like the I2 sequence all the same thing for all those guys. Actually, that's a great way to get really bad sequence diversity on I2 or something, right? If you've got like, if these libraries are high representation themselves, and then together their total is really high representation, those guys are all calling the same sequence in I2 at the same time. That's a great way to drive the base caller to a place you don't want it. But anyway, this is clearly some single index libraries, which is this stripe, mixed in with a smallish, smallish, almost totally dense dual. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 by 3. 10 unique I1s, 3 unique I2s with 29 libraries. This square is actually not a library, but it's like yellowish green. So this I just threw in there just because this is a case where almost certainly there's index hopping going on all within this part. He left out this one square where you can actually see it, and it's there. Now you just don't see it in the rest of them, but this is kind of just illustrates the point. It's if you don't look for it, it's not like it's not happening. It's still there. This is the most dense case you can do and still see one direct observation. Anyway, okay, so we've got 15 minutes left, and we're just at the end of Unity. We've done the all the analysis that we need to do. The last thing to do now is simply to run BCL the best we do and execute the Demux. We completely analyze this thing purposes. So the question is, you have a choice now. You can make a sample sheet that actually targets the full grid, or you can make a sample sheet that just targets the Now, because we've done in R this beautiful analysis with the full grid, you don't really need files for all of those guys. If you're curious what they are, especially if you have other ways of Demux besides the indexes themselves, maybe you do want the files and you can investigate what's going on in the files, or whatever. You can certainly try to Demux. The main thing that drives you crazy, though, trying to do that with BCL test2 is its RAM requirements explode if the number of targets. So if you've got 96 unique dual, you've got 96 distinct I1s, 96 distinct I2s, almost 10,000 cells in the full grid. And BCL test2 will want insane amounts of RAM to do that the way it's designed. And it's just not possible to really do it, at least in one shot. You really do it in batches. I don't recommend people do Demux in batches. BCL test2. I'm not going to have time today to say why that's bad. Yeah, you should basically try to always do Demux in one shot. For kind of the reasons we talked about on day one, is that the mixture is not, although when you cut a target file into pieces, you make it look simpler than it really is. And to the extent that that lets you make decisions you wouldn't have had made from a bigger file, put it this way, in a thought experiment, the logical extreme of dividing a Demux job into smaller pieces is put each sample in its own job. Right? Run BCL with test2 with a 1 and 2 sample sheet for one sample in the lane. Tolerance infinity, place all welds and output files. Right? And it's just, I mean, you've made the sample. I mean, the sample complexity from all the other stuff is still there, whether you think it or not. Now you can arrange for the parameters of BCL test2 that hopefully, like, keep the Demux tolerance the same and so on, like this or whatever. And then you'll get the same outputs as if you really did do it. But what I'm saying is that in general, you can't really, if you change the subset of index cycles you pay attention to, or change the Demux tolerance and things like this, you will change which reads go into which files between doing that in pieces versus doing the job all at once. So yeah, there are cases you can get away with it, but in general, I don't recommend running a Demux job. If you run in pieces, keep a set of cycles that are being paid to exactly the same. Don't use that as a way to handle mixed index formats. And keep your Demux tolerance the same. But anyway, so that's the main disadvantage you can try to do. So it just resource-wise, BCL test2 in one shot is not going to be possible. In that case, just whatever. Just either figure out how to do it in pieces in a way that makes sense, or just go to a sample sheet that just has targets, because your R analysis kind of covers the basis on the hopping matrix and stuff. So anyway, so naming these things kind of a pain. I do recommend sort of having the index merge like we talked about somewhere in the early part of the name. It may also be convenient to actually just have the numbers, just because these are hard to read for humans and stuff. So this is the 13th I1 target with the 7th I2 target. So it kind of, it's a much, for a human, if you're looking at these, whatever, essentially this is in the heat map with cells in. Kind of easy to throw in at the front. it helps you visually compare. You know, I can see that these are all 12 much faster than I can see, you know, the sequence and know what that is. So anyway, but the sample sheet looks like that. If you do full grid, if you just go to the just the identified pairs of the actual samples, it would be much shorter if you do this. But then the command line is exactly what you've already seen. So command line looks just like we already saw. Specify your barcode mismatches. Actually, that's a little slippery. We'll talk about that in a second. You use basis mask. You know, here that's going to be Y1N50, I8, Y1N50, your sample sheet, pointed at your sample sheet. Why is the barcode mismatches a little slippery here? Well, in the R analysis, we kind of applied the mismatch tolerance independently on I1 and I2. These are the test you do more things in terms of put them together into a 16mer and then apply your tolerance. So there can be subtle differences there. I don't want to spend a lot of time getting into those there. Okay, so how about we call it a day for for day 2. We've got a little bit more to do on day 3. I think that'll not be a 3-hour day tomorrow, but we're in the home stretch now. Okay, so I'll stop the Zoom there.